The cosmic microwave background, or CMB, is a faint glow of light that fills the universe, left over from the Big Bang. Discovered in 1965, it provides a snapshot of the infant universe, just 380,000 years old. The CMB is incredibly uniform, but it has slight temperature variations that tell us a lot about the early cosmos. These variations are crucial for understanding the universe's history and structure. One intriguing aspect of the CMB is an anomaly known as the axis of evil. Discovered in 2005, this peculiar alignment challenges our understanding of the cosmos. It refers to a strange pattern in the temperature fluctuations of the CMB that appears to be aligned across the sky. This alignment was unexpected and has sparked much debate among cosmologists. The axis of evil was first noticed when scientists analyzed the dipole and quadrupole components of the CMB. The dipole represents the largest temperature fluctuation, while the quadrupole shows a smaller scale pattern. Surprisingly, these patterns seem to align in a way that defied the random distribution predicted by the standard cosmological model. This alignment raises questions about our assumptions regarding the universe's isotropy and homogeneity. Detecting the axis of evil involved data from several satellite missions, including COBE, WMAP, and Planck. These satellites provided high-precision measurements of the CMB, allowing scientists to identify the anomaly. Advanced statistical methods were used to analyze the data, but the alignment persisted. This consistency across different missions and methods added weight to the findings. The presence of the axis of evil has significant implications for cosmology. If the anomaly is real, it could indicate new physics beyond the standard model. It might suggest modifications to the theory of cosmic inflation, which describes the universe's rapid expansion after the Big Bang. Alternatively, it could hint at previously unknown aspects of dark matter or dark energy. Some scientists propose alternative explanations for the axis of evil. One idea is that the anomaly is caused by foreground contamination, such as emissions from our galaxy interfering with CMB measurements. Others suggest that instrumental errors could account for the alignment. There's also the possibility that the axis of evil is a statistical fluke, a rare but natural occurrence in random data. The role of large-scale structures in the universe is another area of interest. Some researchers think the axis of evil might be connected to the distribution of galaxies and other cosmic structures on a grand scale. Observational evidence and theoretical models are being explored to see if there's a link between these structures and the CMB anomaly. Understanding the axis of evil could impact our measurements of fundamental cosmological parameters. It might influence the value of the Hubble constant, which measures the universe's expansion rate. It could also affect our understanding of the universe's curvature, density, and the distribution of Barion acoustic oscillations. These parameters are crucial for refining our cosmological models. The scientific community remains divided on the significance of the axis of evil. Some view it as a profound mystery that could revolutionize cosmology, while others are more skeptical, attributing it to mundane causes. Recent studies continue to investigate the anomaly, with new data and techniques providing fresh insights. The debate is ongoing, and future research will be key to resolving it. Public interest in the axis of evil has grown, with media coverage bringing the anomaly to a wider audience. However, this has also led to misconceptions. It's important to communicate the science accurately, helping people understand both the potential significance and the current uncertainties. Engaging the public in these discussions can inspire future generations of scientists. Future research and upcoming satellite missions hold promise for unraveling the mystery of the axis of evil. Advances in observational technology and data analysis methods will enhance our ability to study the CMB in greater detail. International collaborations and new theoretical models will also play a crucial role. As we continue to explore the cosmos, we may uncover answers that shed light on this cosmic enigma. The cosmic microwave background, often abbreviated as CMB, represents the afterglow of the Big Bang, the colossal explosion that birthed our universe. This faint microwave radiation permeates the entire cosmos, providing a crucial glimpse into its earliest moments. The CMB is essentially the oldest light we can observe, dating back nearly 13.8 billion years. The discovery of the CMB was serendipitous, happening in 1965 when two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon it while working at the Bell Telephone Laboratories in New Jersey. They were using a sensitive horn antenna designed for satellite communications and were puzzled by a persistent noise that seemed to come from all directions. This noise, which they couldn't eliminate, turned out to be the cosmic microwave background radiation. Their discovery was a pivotal moment in cosmology, providing compelling evidence for the Big Bang theory. The CMB confirmed that the universe had a hot and dense origin, supporting the idea that it has been expanding and cooling ever since. For their groundbreaking work, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, cementing the CMB's importance in understanding the universe's origins. The CMB is remarkably uniform, but it contains tiny fluctuations in temperature that are crucial for studying the early universe. These fluctuations, or anisotropies, are only about 1 part in 100,000. They represent slight variations in density from which all the structures in the universe, such as galaxies and clusters of galaxies, eventually formed. The study of these anisotropies provides a wealth of information about the universe's composition, age, and evolution. Observations of the CMB have been greatly enhanced by satellite missions. The first major mission, COBE, launched by NASA in 1989, mapped the CMB with unprecedented precision. COBE's findings confirmed the CMB's blackbody spectrum and detected the temperature fluctuations for the first time. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided even more detailed measurements, further refining our understanding of the early universe. The most recent and detailed observations come from the Planck satellite, launched by the European Space Agency in 2009. Planck has provided the highest resolution map of the CMB to date, allowing scientists to study its anisotropies with incredible detail. The data from Planck has been instrumental in refining cosmological parameters, such as the age of the universe and the density of its various components. The CMB's uniformity and slight temperature variations are crucial for understanding the universe's large-scale structure. These minute differences in temperature correspond to regions of slightly different densities in the early universe. Over billions of years, these density variations grew into the galaxies, clusters, and voids we observe today. Thus, the CMB acts as a cosmic blueprint, showing us the seeds from which all cosmic structures have grown. In addition to temperature fluctuations, the CMB also contains information about polarization, which provides insights into the universe's early conditions and the formation of the first stars and galaxies. Polarization measurements can reveal the influence of gravitational waves, giving us clues about the very first moments of the universe's existence. Understanding these aspects of the CMB helps scientists piece together a more complete picture of cosmic history. The study of the CMB also sheds light on fundamental aspects of physics. By analyzing the CMB, scientists can test theories about the universe's geometry, the nature of dark matter and dark energy, and the physics of the early universe. The CMB's detailed map acts like a cosmic laboratory, allowing researchers to probe conditions and phenomena that cannot be replicated on Earth. One intriguing feature of the CMB is its near-perfect blackbody spectrum, which indicates that it has been through a process of thermalization. This means that, in the early universe, all particles and photons were in thermal equilibrium, a state that was maintained until the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This period, known as recombination, allowed photons to travel freely through space, creating the CMB we observe today. The temperature of the CMB today is a chilly 2.725 Kelvin, just above absolute zero. This temperature has cooled from its original hot state, due to the expansion of the universe. Measuring the CMB's temperature and its variations helps cosmologists understand how the universe has expanded and evolved over billions of years. It's like a cosmic thermometer, providing vital clues about the universe's past. The discovery and study of the CMB have also had profound implications for cosmological theories. It has helped confirm the Big Bang model and has provided a framework for understanding the universe's subsequent development. Without the CMB, many aspects of our cosmological models would remain speculative. The CMB serves as a cornerstone of modern cosmology, anchoring our theories in observable evidence. While the CMB's primary significance lies in its support for the Big Bang theory, it also poses new questions and challenges. The detailed study of its anisotropies has revealed subtle anomalies, such as the aforementioned axis of evil, that defy simple explanations. These anomalies suggest that there might be more to learn about the universe's structure and evolution, possibly pointing to new physics beyond our current understanding. The CMB continues to be a fertile field for research, with new data and analyses continually refining our understanding of the cosmos. As technology advances, future missions and instruments will provide even more precise measurements, unveiling new details about the universe's infancy. The study of the CMB is a dynamic and evolving field, offering the potential for groundbreaking discoveries in the years to come. The cosmic microwave background is a cornerstone in the field of cosmology, providing a wealth of information about the universe's origins and evolution. It acts as a snapshot of the early universe, offering a direct view of conditions just 380,000 years after the Big Bang. This makes the CMB an invaluable tool for testing cosmological theories and models. One of the primary reasons the CMB is so crucial is that it contains the imprint of the universe's initial conditions. The tiny temperature fluctuations within the CMB reveal the distribution of matter and energy in the early universe. These fluctuations eventually led to the formation of all the large-scale structures we see today, including galaxies, clusters, and superclusters. By studying the CMB, cosmologists can determine the age of the universe with remarkable precision. Current estimates, based on CMB data, place the age of the universe at approximately 13.8 billion years. This age determination is critical for understanding the timeline of cosmic events and the development of various structures within the universe. The CMB also provides crucial insights into the universe's geometry. Measurements of the CMB's temperature fluctuations allow scientists to determine whether the universe is flat, open, or closed. The data strongly suggest that the universe is flat, which has significant implications for cosmological models and theories about the universe's fate. Another key aspect of the CMB's importance is its role in confirming the Big Bang theory. Before the discovery of the CMB, there were competing theories about the origin of the universe, such as the steady-state theory. The CMB's existence and properties provided strong evidence for the Big Bang model, helping to establish it as the dominant explanation for the universe's beginnings. The CMB's detailed observations have also led to the development of the standard model of cosmology, known as the lambda cold dark matter model, or lambda CDM. This model describes a universe composed of ordinary matter, and dark energy. It explains the observed large-scale structure of the universe and its accelerating expansion, all supported by CMB data. Dark matter and dark energy, two of the most mysterious components of the universe, are better understood through the study of the CMB. The CMB data provide constraints on the amount and distribution of dark matter and dark energy, helping scientists to refine their models and theories about these elusive substances. This understanding is crucial for comprehending the overall dynamics and evolution of the cosmos. The polarization of the CMB adds another layer of valuable information. By analyzing the CMB's polarization patterns, scientists can gain insights into the universe's early moments and the formation of the first stars and galaxies. Polarization data can also provide evidence for the presence of gravitational waves from the early universe, offering a glimpse into the physics of the very first fractions of a second after the Big Bang. The CMB also helps to constrain the parameters of inflation, a rapid expansion of the universe that occurred a fraction of a second after the Big Bang. The precise measurements of the CMB's temperature and polarization fluctuations provide evidence supporting the inflationary model, helping to refine our understanding of this critical period in cosmic history. Cosmologists use the CMB to study the composition of the universe. The data reveal the relative amounts of ordinary matter, and dark energy. This composition is crucial for understanding how the universe has evolved over time and how different forces have shaped its large-scale structure. The CMB thus serves as a cosmic census, detailing the universe's fundamental constituents. The CMB's importance extends to its ability to test fundamental physical theories. The data from the CMB allow scientists to test predictions from general relativity and quantum mechanics on cosmological scales. These tests are vital for verifying our understanding of the laws of physics and identifying any potential new physics that might arise from discrepancies between theory and observation. One of the most exciting aspects of CMB research is its potential to uncover new physics. While the current data mostly fit within existing models, there are still unexplained anomalies and features that could point to new phenomena. Continued study of the CMB might reveal unexpected insights into the nature of the universe and the laws governing it. The CMB also serves as a bridge between observational and theoretical cosmology. It provides a wealth of precise data that theorists use to develop and refine models of the universe. This synergy between observation and theory is essential for advancing our understanding of cosmology and making progress in solving some of the field's biggest questions. Furthermore, the CMB has been instrumental in fostering international collaboration in cosmology. Large-scale missions like COBE, WMAP, and Planck involve scientists from around the world working together to analyze the data and interpret the results. This collaborative effort has led to significant advancements in our understanding of the universe and has driven the field forward. The importance of the CMB in cosmology cannot be overstated. It provides a direct link to the universe's earliest moments, offering a wealth of information that helps to unravel the mysteries of the cosmos. As new data and techniques become available, the CMB will continue to play a central role in our quest to understand the universe and our place within it. The cosmic microwave background is a pervasive field of microwave radiation that fills the entire universe. It is remarkably uniform, but it contains tiny fluctuations in temperature. These temperature variations are only about 1 part in 100,000, making them incredibly subtle but extremely important for cosmologists. The average temperature of the CMB today is approximately 2.725 Kelvin, just above absolute zero. This temperature is the same in all directions, indicating that the early universe was in a state of thermal equilibrium. The slight deviations from this average temperature provide a snapshot of the density fluctuations in the early universe. The CMB has a nearly perfect blackbody spectrum, which is the thermal radiation profile emitted by an idealized, perfectly emitting body. This blackbody spectrum confirms that the CMB originates from a hot, dense state, supporting the Big Bang theory. The peak of this spectrum falls in the microwave range, which is why it is observed using microwave telescopes. One of the most notable properties of the CMB is its isotropy, meaning it looks almost the same in every direction. This uniformity suggests that the universe was extremely homogeneous and isotropic on large scales shortly after the Big Bang. However, the small anisotropies, or temperature fluctuations, are critical for understanding the universe's large-scale structure. The anisotropies in the CMB are a rich source of information. They are caused by slight differences in the density and temperature of the primordial plasma from which the CMB originated. These fluctuations were seeded by quantum fluctuations during inflation, the rapid expansion of the universe that occurred a fraction of a second after the Big Bang. The angular power spectrum of the CMB is a tool used to describe the temperature fluctuations on different scales. Peaks in this spectrum correspond to different physical processes in the early universe. The first peak, for example, is related to the density of normal matter, while the second and third peaks provide information about the density of dark matter and the geometry of the universe. Polarization is another critical property of the CMB. The CMB is partially polarized due to Thomson scattering, which occurred when the universe was Rayonized by the first stars. Polarization measurements can reveal information about the early universe's reionization history and the presence of primordial gravitational waves. The CMB also shows a dipole anisotropy, a temperature difference between two opposite directions in the sky. This dipole is primarily due to the motion of our solar system relative to the rest of the universe. By measuring this dipole, scientists can determine our velocity and direction through space. The Sunyaev-Zeldovich effect is another important feature observed in the CMB. This effect occurs when CMB photons interact with hot electrons in galaxy clusters, causing a distortion in the CMB's spectrum. By studying this effect, scientists can learn about the properties of galaxy clusters and the distribution of matter in the universe. The integrated Sachs-Wolf effect is a phenomenon where the CMB's temperature is altered by the gravitational potential of large-scale structures. This effect provides insights into the distribution of dark matter and the dynamics of the universe's expansion. It is observed as slight temperature variations correlated with large-scale structures. Gravitational lensing is another property that affects the CMB. As CMB photons travel through the universe, their paths are bent by the gravitational fields of massive objects. This lensing effect smears out the temperature fluctuations, providing information about the distribution of matter along the line of sight and the total mass in the universe. The CMB's detailed maps have revealed unexpected anomalies, such as the cold spot, an unusually large and cold region. These anomalies are intriguing because they could indicate new physics or unaccounted-for structures in the universe. Understanding these anomalies remains an active area of research. Planck, WMAP, and COBE have provided the most detailed maps of the CMB to date. These missions have measured the CMB's temperature and polarization with unprecedented accuracy. The data from these missions have been crucial for refining cosmological models and understanding the universe's fundamental properties.
Future missions aim at CMB with even greater precision. Projects like the Simons Observatory and CMB-S4 will provide more detailed measurements of the CMB temperature and polarization. These observations will help answer outstanding questions about the early universe and the nature of dark matter and dark energy.
The CMB's properties make it an essential tool for cosmologists. It provides a direct link to the universe's earliest moments, allowing scientists to probe conditions that existed shortly after the Big Bang. By studying the CMB, we can learn about the universe's age, composition, and evolution, making it one of the most valuable sources of information in modern cosmology. The journey to discovering the cosmic microwave background began with early radio astronomy observations. In the 1940s and 50s, scientists used radio telescopes to study the sky, but they didn't initially detect the CMB. The technology of the time wasn't sensitive enough to pick up this faint microwave radiation. The pivotal discovery happened in 1965, thanks to Arno Penzias and Robert Wilson at Bell Telephone Laboratories. They were working with a large horn antenna designed for satellite communication experiments. While trying to eliminate background noise from their measurements, they stumbled upon a persistent hiss that seemed to come from every direction. Penzias and Wilson initially suspected various sources for this noise, including urban interference, equipment issues, and even pigeon droppings in the antenna. After ruling out these possibilities, they consulted with physicists who had predicted the existence of the CMB. These predictions were based on theoretical models of the early universe.
Team at Princeton University, led by Robert Dicke, was preparing to search the CMB. When they heard about Penzias and Wilson's unexplained noise, they immediately recognized it as predicted radiation. This serendipitous discovery provided strong evidence for the Big Bang theory and earned Penzias and Wilson the Nobel Prize.
The initial observations by Penzias and Wilson indicated a uniform microwave background with a temperature of about 3 Kelvin. This uniformity was a significant confirmation of the Big Bang model, suggesting a hot, dense origin of the universe that has since expanded and cooled. The discovery was a turning point in cosmology, shifting the scientific consensus towards the Big Bang theory. Subsequent observations aimed to measure the CMB with greater precision and detail. In the 1970s, the Cosmic Background Explorer, or COBE, mission was developed to map the CMB. Launched in 1989, COBE provided the first detailed measurements of the CMB's temperature and its tiny fluctuations. These fluctuations were crucial for understanding the large-scale structure of the universe. COBE's findings were groundbreaking. The satellite confirmed the CMB's blackbody spectrum, which matched the theoretical predictions for radiation from the early universe. COBE also detected minute temperature variations across the sky, revealing the seeds of future galaxy formation. These results earned John Mather and George Smoot the Nobel Prize in Physics in 2006. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, offered even more detailed observations. WMAP provided high-resolution maps of the CMB, measuring temperature fluctuations with unprecedented accuracy. The data from WMAP allowed cosmologists to refine their models of the universe and better understand its composition and age. WMAP's observations led to several key findings. It confirmed the universe's age at approximately 13.8 billion years and provided precise measurements of the universe's composition, including the proportions of dark matter, dark energy, and ordinary matter. These measurements have been critical for developing the lambda CDM model, the standard model of cosmology. The Planck satellite, launched by the European Space Agency in 2009, represented the next leap in CMB observations. Planck's mission was to map the CMB with even greater precision than its predecessors. The data from Planck have provided the most detailed picture of the CMB to date, further refining cosmological parameters and enhancing our understanding of the early universe. Planck's results have been instrumental in confirming and expanding upon the findings of COBE and WMAP. The high-resolution maps of temperature and polarization fluctuations have allowed scientists to study the CMB in unprecedented detail. These observations have shed light on the universe's inflationary period and the distribution of dark matter and dark energy. One of the key findings from Planck is the confirmation of the universe's flat geometry. The detailed analysis of the CMB's temperature fluctuations supports the idea that the universe is spatially flat, aligning with predictions from the inflationary Big Bang model. This geometric insight is crucial for understanding the universe's overall structure and fate. Planck also provided insights into the reionization of the universe. The polarization measurements indicated that reionization, the process where the first stars and galaxies ionize the intergalactic medium, occurred later than previously thought. This finding has implications for the timeline of cosmic structure formation. The observations from these missions have consistently supported the Big Bang model and the theory of cosmic inflation. The detailed study of the CMB's temperature and polarization patterns has helped refine the parameters of inflation, providing a deeper understanding of the rapid expansion that shaped the early universe. The ongoing analysis of CMB data continues to reveal new insights and refine our cosmological models. Future missions and technological advancements promise to further enhance our understanding of the CMB and its implications for cosmology. Each new discovery builds on the foundation laid by these initial observations, driving our exploration of the universe's origins and evolution. While the cosmic microwave background is remarkably uniform, it contains subtle anomalies that have puzzled scientists. These anomalies are small deviations from the expected temperature fluctuations and patterns. They challenge our understanding of the early universe and the fundamental laws of physics. One of the most famous anomalies is the axis of evil. This refers to a peculiar alignment of temperature fluctuations in the CMB. These fluctuations appear to be oriented along a specific direction in the sky, which is unexpected based on standard cosmological models. The axis of evil was first noticed in the early 2000s and has sparked significant debate among cosmologists. Another notable anomaly is the cold spot. This is an unusually large and cold region in the CMB, located in the southern hemisphere of the sky. The cold spot is much larger and more significant than the typical temperature fluctuations seen in the CMB. Its existence has led to various hypotheses, including the possibility of a supervoid or even more exotic explanations, like a collision with another universe. The lack of large-scale power in the CMB is also an anomaly. Theoretical models predict certain levels of temperature fluctuations on large scales, but observations show a deficit in these fluctuations. This discrepancy suggests there may be aspects of the early universe or our cosmological models that we do not fully understand. Anomalies in the CMB's polarization patterns have also been observed. These patterns should be random and isotropic, but certain alignments and features have been detected that deviate from this expectation. Studying these anomalies could provide insights into the universe's reionization history and the influence of primordial gravitational waves. The hemispherical asymmetry is another intriguing anomaly. It refers to a difference in the average temperature fluctuations between the northern and southern hemispheres of the CMB. This asymmetry challenges the assumption that the universe is isotropic on large scales and could indicate new physics or systematic effects that need to be understood. The presence of the CMB dipole, primarily due to our motion relative to the CMB, is expected, but higher-order multipoles, such as the quadrupole and octopole, show unexpected alignments. These alignments suggest a preferred direction in the universe, which contradicts the cosmological principle that the universe should be isotropic and homogeneous on large scales. Foreground contamination from our galaxy and other sources can complicate the analysis of the CMB. Separating these foregrounds from the true CMB signal is challenging and can introduce uncertainties and potential anomalies. Advanced data processing techniques are continuously being developed to minimize these effects. The anomalies observed in the CMB are not easily explained by the standard model of cosmology. They may require new theoretical models or modifications to existing ones. These could include changes to the inflationary model, new forms of matter or energy, or even the influence of higher dimensions. Cosmic inflation is a leading theory to explain the uniformity and structure of the CMB. However, certain anomalies might suggest modifications to this theory. For example, multi-field inflation or alternative inflationary scenarios could potentially account for some of the observed deviations in the CMB. Some anomalies might be statistical flukes. Given the vast amount of data and the complexity of the CMB, it is possible that some of the anomalies are simply due to random variations or noise. Rigorous statistical analysis is necessary to determine which anomalies are significant and which are not. Exotic theories have been proposed to explain some of the CMB anomalies. These include the idea of a multiverse, where our universe has interacted with other universes, leaving imprints on the CMB. Another theory involves cosmic textures, defects in the fabric of space-time that could create cold spots and other features. The anomalies could also provide clues about dark matter and dark energy. Understanding these mysterious components of the universe is a major goal of cosmology, and the CMB anomalies might offer indirect evidence about their properties and interactions. This could lead to breakthroughs in our understanding of the universe's composition and dynamics. Continued study of the CMB anomalies is essential. New missions, such as the Simons Observatory and future CMB-S4, will provide even more detailed observations of the CMB. These missions aim to resolve existing anomalies and potentially discover new ones, furthering our understanding of the early universe. Each new anomaly discovered in the CMB adds a piece to the puzzle of cosmology. By investigating these anomalies, scientists hope to uncover deeper truths about the universe's origins, its current state, and its ultimate fate. The study of CMB anomalies is a dynamic and evolving field that promises to yield exciting discoveries in the years to come. The axis of evil is a term used to describe a strange alignment in the cosmic microwave background, or CMB. This alignment appears in the temperature fluctuations of the CMB, which are typically expected to be random and isotropic. However, the axis of evil suggests a preferred direction in the universe, challenging this expectation. The term was coined in the early 2000s when researchers first noticed this unusual pattern. They observed that the largest scales of the CMB, particularly the quadrupole and octopole moments, were not oriented randomly. Instead, these moments seemed to align along a specific axis, which was unexpected and puzzling. The name axis of evil was chosen partly in jest, playing on the phrase popularized by then US President George W. Bush. In the context of cosmology, it highlights the troubling nature of this alignment for the standard model of cosmology. The axis of evil implies that the universe might have a preferred direction, contradicting the cosmological principle that the universe is isotropic and homogeneous on large scales. This alignment is significant because it could indicate new physics or previously unconsidered effects. The standard model of cosmology, based on the Big Bang theory and cosmic inflation, predicts a highly uniform and random distribution of temperature fluctuations in the CMB. The axis of evil's alignment suggests there might be more to the story. Scientists have proposed several explanations for the axis of evil. One possibility is that it results from local foreground contamination, such as emissions from our galaxy. However, extensive efforts to remove such foregrounds from the data have not eliminated the alignment, suggesting it might be intrinsic to the CMB itself. Another hypothesis is that the axis of evil could be a statistical fluke. Given the vast amount of data, some anomalies might occur purely by chance. However, the persistence of this alignment across different datasets and analysis methods makes it less likely to be a mere coincidence. Some researchers have suggested that the axis of evil might point to new physics. For instance, it could indicate anisotropies in the early universe that are not accounted for by the standard inflationary model. These anisotropies might arise from exotic phenomena such as topological defects or interactions with other universes. Another intriguing possibility is that the axis of evil could be a sign of large-scale cosmic structures influencing the CMB. For example, massive superclusters or voids could imprint their signatures on the CMB, creating the observed alignment. Understanding these potential structures could provide insights into the large-scale distribution of matter in the universe. The axis of evil has also been linked to the idea of cosmic variance. Cosmic variance refers to the statistical uncertainty inherent in measurements of the universe on large scales. The observed alignment might be a manifestation of this variance, though it remains an open question whether this can fully account for the axis of evil. Some theories suggest that the axis of evil could be related to the universe's shape or topology. If the universe has a non-trivial topology, such as being shaped like a torus or other complex structure, this could create preferred directions and alignments in the CMB. This idea challenges conventional views of the universe's geometry. The discovery of the axis of evil has spurred further research into the fundamental properties of the universe. Scientists are exploring whether similar alignments or anomalies exist in other cosmic observations, such as the distribution of galaxies or large-scale flows of matter. These studies aim to determine whether the axis of evil is a unique feature of the CMB or part of a broader pattern. Efforts to understand the axis of evil have also led to advances in data analysis techniques. Researchers are developing new methods to filter out potential sources of contamination and improve the accuracy of CMB measurements. These advancements enhance our ability to study the universe's earliest moments and its large-scale structure. The debate over the axis of evil highlights the dynamic nature of cosmology. As new data becomes available from current and future missions, scientists will continue to test and refine their theories. The axis of evil remains a topic of intense scrutiny and discussion, driving progress in our understanding of the cosmos. The significance of the axis of evil extends beyond the specific alignment itself. It raises fundamental questions about the assumptions underlying our cosmological models. If the universe does have a preferred direction, this would have profound implications for our understanding of its origins, evolution, and ultimate fate. As research into the axis of evil continues, it exemplifies the spirit of scientific inquiry. Anomalies like this challenge our current theories and push us to explore new ideas and possibilities. Whether the axis of evil ultimately leads to a major paradigm shift or a deeper understanding within the existing framework, it represents a fascinating frontier in cosmology. The discovery of the axis of evil in the cosmic microwave background was a significant moment in cosmology, arising from detailed analysis of data collected by satellite missions. It all began with the launch of the Cosmic Background Explorer, or COBE, in 1989. COBE provided the first high-resolution maps of the CMB, revealing minute temperature fluctuations that offered clues about the early universe. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in 2001. WMAP's mission was to create even more detailed maps of the CMB, measuring temperature fluctuations with unprecedented accuracy. The data from WMAP played a crucial role in the discovery of the axis of evil, as it provided a clearer picture of the large-scale anomalies in the CMB. In the early 2000s, researchers analyzing WMAP data noticed an unusual alignment of the quadrupole and octupole moments. These moments represent large-scale temperature fluctuations in the CMB, and their alignment suggested a preferred direction in the sky. This discovery was surprising because the standard cosmological model predicts that such fluctuations should be randomly distributed. The term axis of evil was first used in a paper published in 2005 by Kate Land and João Maguejo. They highlighted the alignment as a significant anomaly that could challenge our understanding of the universe. The name was chosen partly for its provocative nature, emphasizing the troubling implications of the alignment for conventional cosmological theories. The discovery of the axis of evil prompted further investigations into the nature of this alignment. Researchers began to explore whether it could be an artifact of data processing or a result of foreground contamination from our galaxy. Despite these efforts, the alignment persisted across different datasets and analysis methods, suggesting it might be a real feature of the CMB. As more data became available from subsequent missions, including the Planck satellite launched in 2009, the evidence for the axis of evil grew stronger. Planck provided the most detailed maps of the CMB to date, confirming the alignment seen in WMAP data. This consistency across different missions reinforced the idea that the axis of evil was not a mere statistical fluke. The historical context of this discovery is important because it highlights the evolution of our understanding of the universe. The detection of the CMB itself in 1965 by Arno Penzias and Robert Wilson was a landmark event, providing strong evidence for the Big Bang theory. Subsequent missions like COBE, WMAP, and Planck have built on this foundation, revealing increasingly detailed information about the early universe. The discovery of the axis of evil came at a time when the standard model of cosmology, known as lambda cold dark matter or lambda CDM, was widely accepted. This model successfully explained a wide range of observations, including the overall structure and composition of the universe. However, the axis of evil suggested there might be aspects of the universe that this model does not fully capture. The alignment observed in the CMB challenged the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. This principle is a cornerstone of modern cosmology, underpinning many theoretical models and interpretations of observational data. The axis of evil called into question the assumption that the universe has no preferred directions. The historical significance of the axis of evil also lies in its potential to inspire new theories and models. If the alignment is indeed a real feature of the universe, it could indicate new physics or phenomena that are not accounted for in the standard model. This possibility has motivated researchers to explore a wide range of hypotheses, from modifications to inflation theory to the existence of multiple universes. The discovery process of the axis of evil involved sophisticated data analysis techniques. Researchers used statistical methods to identify and characterize the alignment, carefully accounting for potential sources of error and bias. This meticulous approach has been crucial for establishing the credibility of the findings and understanding their implications. As the debate over the axis of evil continued, it spurred advancements in cosmological research and data analysis. Scientists developed new tools and methods to study the CMB and other cosmic phenomena, improving our ability to detect and interpret subtle anomalies. These advancements have had broader impacts on the field, enhancing our overall understanding of the universe. The ongoing study of the axis of evil highlights the dynamic nature of scientific inquiry. Each new discovery raises questions and challenges existing theories, driving the search for deeper understanding. The axis of evil remains a topic of active research and debate, with new data and analyses continually contributing to the discussion. In the broader context of cosmology, the discovery of the axis of evil is a reminder of the complexities and mysteries that still lie ahead. Despite the significant progress made in recent decades, there is much we do not yet know about the universe. Anomalies like the axis of evil provide valuable opportunities to expand our knowledge and refine our theories. Key researchers and studies have played crucial roles in uncovering and analyzing the axis of evil in the cosmic microwave background. Among the first to bring attention to this anomaly were Kate Land and João Magalhães. Their 2005 paper highlighted the unexpected alignment of the quadrupole and octupole moments in the CMB, coining the term axis of evil. Another significant contributor to the study of the axis of evil is Max Tegmark. Tegmark, along with his collaborators, conducted detailed analyses of CMB data, focusing on large-scale anomalies. His work helped to confirm the presence of the alignment and raised important questions about its implications for cosmology. Researchers at Princeton University, including David Spergel and his team, have also made substantial contributions. They were heavily involved in the WMAP mission, which provided critical data for identifying and studying the axis of evil. Their analyses helped to refine our understanding of the CMB and its anomalies. The Planck collaboration, an international team of scientists working with the European Space Agency's Planck satellite data, has provided some of the most detailed observations of the CMB. Their work has been instrumental in confirming and expanding upon earlier findings related to the axis of evil, using high-resolution maps of the CMB's temperature and polarization. Anthony Banday and Krzysztof Gorski have conducted extensive research on the CMB, focusing on its large-scale structure and anomalies. Their studies have examined the statistical significance of the axis of evil, exploring whether it could be a result of data processing or an inherent feature of the universe. Researchers such as Glenn Starkman have explored the theoretical implications of the axis of evil. Starkman's work has included investigating potential explanations for the alignment, from local foreground effects to new physics beyond the standard cosmological model. His contributions have helped to frame the ongoing debate about the anomaly. The contributions of George Evstathiou cannot be overlooked. Evstathiou has been a leading figure in the analysis of CMB data and the interpretation of cosmological observations. His work with the Planck collaboration has been particularly influential in understanding the statistical and theoretical context of the axis of evil. Another key figure is André Linde, a prominent theoretical physicist known for his work on cosmic inflation. Linde's insights into inflationary models have provided a framework for interpreting anomalies in the CMB, including the axis of evil. His theoretical contributions continue to influence how researchers approach these cosmic puzzles. Krauss's research has explored how this alignment might affect our understanding of the universe's geometry and the fundamental principles of cosmology. His work highlights the broader impacts of this anomaly on cosmological theories. Ned Wright, a key member of the WMAP and COBE teams, has provided significant contributions to the study of the CMB. Wright's expertise in data analysis and interpretation has been vital for identifying and understanding the axis of evil, as well as other large-scale features of the CMB. John Kovacs and his team at the BICEP and Keck array experiments have focused on measuring the polarization of the CMB. Their work is crucial for understanding the potential connections between the axis of evil and primordial gravitational waves, providing deeper insights into the early universe. Researchers like Dominic Schwartz have examined the cosmological implications of the axis of evil. Schwartz's studies have looked into how this anomaly fits into the broader picture of cosmic structure and what it might reveal about the universe's initial conditions. Matthias Zaldariaga has made important contributions to the theoretical understanding of the CMB. His work on the statistical properties of CMB fluctuations has helped to contextualize the significance of the axis of evil and its potential origins. Charles Bennett, the principal investigator for the WMAP mission, has overseen some of the most detailed observations of the CMB. Bennett's leadership and expertise have been critical in producing the high-quality data needed to study the axis of evil and other anomalies. Finally, the contributions of researchers like Gary Hinshaw, who have been involved in both the WMAP and Planck missions, are vital. Hinshaw's work in data analysis and interpretation continues to shape our understanding of the CMB, providing the foundation for ongoing research into the axis of evil and its implications for cosmology. The initial reactions from the scientific community to the discovery of the axis of evil were mixed. Some researchers were intrigued by the potential implications of such an alignment, while others were skeptical, considering it might be a statistical anomaly or an artifact of data processing. When the axis of evil was first reported, it generated significant interest among cosmologists. Many scientists were eager to explore the potential explanations for this unexpected alignment. The possibility that it could indicate new physics or a deeper understanding of the universe was a compelling motivation for further study. Skepticism was also prevalent, with some researchers questioning the validity of the findings. They argued that the alignment could be the result of systematic errors in the data or the methods used to analyze it. This skepticism prompted a thorough re-examination of the data to rule out potential biases. The debate over the axis of evil highlighted the importance of rigorous statistical analysis in cosmology. Researchers scrutinized the methods used to detect and characterize the alignment, seeking to ensure that the results were robust and reliable. This scrutiny led to the development of more sophisticated techniques for analyzing CMB data. Some scientists suggested that the axis of evil might be explained by local foreground contamination. They proposed that emissions from our galaxy or other nearby sources could create apparent alignments in the CMB. This hypothesis led to extensive efforts to separate foreground signals from the true CMB data. Despite these efforts, the axis of evil remained a persistent feature in the data. The consistency of the alignment across different datasets and analysis methods suggested that it was not simply a result of foreground contamination or statistical flukes. This persistence kept the debate alive and fueled ongoing research. The initial skepticism also led to a broader discussion about the nature of anomalies in cosmological data. Researchers considered whether other anomalies might exist and how they should be interpreted. This discussion helped to frame the axis of evil within the larger context of cosmological research. Some scientists embraced the anomaly as a potential clue to new physics. They argued that if the axis of evil were real, it could provide insights into the early universe and the fundamental forces that shaped it. This perspective encouraged the exploration of alternative cosmological models and theories. The discovery of the axis of evil also prompted a re-evaluation of the cosmological principle. If the universe did have a preferred direction, this would challenge the long-held assumption that it is isotropic and homogeneous on large scales. This potential paradigm shift was both exciting and controversial. As more data became available from missions like Planck, the scientific community continued to investigate the axis of evil. Some researchers remained skeptical, while others became more convinced of its significance. The ongoing analysis of new data was crucial for resolving these differing perspectives. The initial reactions also highlighted the importance of collaboration in cosmology. Scientists from different institutions and disciplines worked together to understand the axis of evil, sharing data, methods, and insights. This collaborative approach was essential for making progress on this complex problem. Publications and presentations on the axis of evil sparked lively discussions at conferences and in academic journals. These forums provided opportunities for researchers to present their findings, critique each other's work, and propose new ideas. The scientific community's engagement with the anomaly was both rigorous and dynamic. Some researchers proposed that the axis of evil could be a window into higher dimensional physics or other exotic phenomena. These speculative ideas pushed the boundaries of conventional cosmological theories and opened new avenues for theoretical exploration. The willingness to consider bold hypotheses was a testament to the creativity and curiosity of the scientific community. The persistence of the axis of evil in the face of skepticism underscored the importance of open-mindedness in scientific inquiry. While some initial reactions were dismissive, the continued presence of the anomaly in new data forced scientists to reconsider their positions and explore all possible explanations. Ultimately, the initial reactions to the axis of evil reflected the dynamic nature of scientific progress. The discovery challenged existing paradigms, sparked debate, and motivated new research. It illustrated how anomalies can drive the search for deeper understanding and lead to significant advancements in our knowledge of the universe. The significance of the axis of evil lies in its potential to challenge and reshape our understanding of the universe. This alignment in the cosmic microwave background suggests that there might be underlying principles or phenomena not accounted for by the standard cosmological model. If the axis of evil is a genuine feature of the universe, it could imply that the universe is not isotropic on large scales. This would challenge the cosmological principle, which assumes that the universe is the same in all directions when viewed on a sufficiently large scale. Such a finding would have profound implications for cosmological theories. The alignment may indicate the presence of new physics beyond the current models. It could point to previously unknown forces or interactions that influenced the early universe. Understanding these forces could lead to a deeper comprehension of the fundamental laws of nature. One of the most intriguing possibilities is that the axis of evil could be a signature of cosmic inflation. If so, it might provide insights into the inflationary period that occurred a fraction of a second after the Big Bang. This could help refine our models of how inflation shaped the structure of the universe. The axis of evil might also offer clues about the large-scale structure of the universe. If massive structures or voids are responsible for the alignment, studying these features could reveal new information about the distribution of matter and energy on cosmic scales. This would enhance our understanding of the universe's evolution. This anomaly could also affect our measurements of cosmological parameters. Parameters such as the Hubble constant, dark matter density, and dark energy properties might need to be re-evaluated in light of the axis of evil. Accurate measurements of these parameters are crucial for refining our models of the universe. The axis of evil has sparked interest in the possibility of a multiverse. If our universe is one of many, interactions with other universes could leave imprints on the CMB. Investigating this idea could open new avenues of research in theoretical physics and cosmology. The presence of the axis of evil could influence the development of new observational techniques. Researchers may devise innovative methods to detect and analyze similar anomalies, improving our ability to study the universe. This could lead to technological advancements in telescopes and data analysis tools. Exploring the axis of evil helps foster interdisciplinary collaboration. Physicists, astronomers, and mathematicians work together to understand this anomaly, combining their expertise to tackle complex questions. Such collaboration enriches the scientific community and drives progress. The significance of the axis of evil extends to its impact on public interest in cosmology. Anomalies like this capture the imagination and curiosity of people, inspiring a broader interest in scientific exploration. Public engagement with such topics can support education and research funding. If the axis of evil is linked to new forms of matter or energy, it could provide insights into dark matter and dark energy. These mysterious components make up most of the universe, yet remain poorly understood. The axis of evil could be a key to unlocking some of these mysteries. The alignment also highlights the importance of precision in cosmological measurements. Small anomalies can have significant implications, underscoring the need for accurate and detailed observations. This drives the development of more advanced instruments and methodologies. The study of the axis of evil encourages a critical examination of existing theories. It prompts scientists to re-evaluate and test the assumptions underlying their models, fostering a healthy scientific skepticism that is essential for progress. This rigorous scrutiny helps refine and improve our understanding of the universe. The axis of evil could influence future theoretical work. The need to explain this anomaly might lead to the development of new theories or modifications of existing ones. This theoretical innovation is a vital part of scientific advancement, pushing the boundaries of what we know. Ultimately, the significance of the axis of evil lies in its ability to inspire deeper inquiry. Whether it leads to a major paradigm shift or helps refine current models, the study of this anomaly exemplifies the dynamic and evolving nature of cosmology. It represents an ongoing quest to understand the universe and our place within it. The CMB dipole is one of the most prominent features observed in the cosmic microwave background. It represents the largest temperature fluctuation in the CMB, caused primarily by the motion of our solar system relative to the rest of the universe. This motion creates a Doppler shift, resulting in a temperature difference between two opposite directions in the sky. The dipole anisotropy was one of the first features detected in the CMB. It shows a temperature variation of about 3 millikelvin, which is significantly larger than the tiny fluctuations seen on smaller scales. This large-scale anisotropy is a direct consequence of our movement through space. The direction of the dipole indicates the velocity and direction of our solar system's motion. We are moving towards the constellation Leo at a speed of approximately 370 kilometers per second. This motion causes the CMB to appear slightly hotter in the direction of our movement and cooler in the opposite direction. Understanding the CMB dipole is crucial for cosmological measurements. By accounting for this motion, scientists can correct for its effects and study the intrinsic properties of the CMB with greater accuracy. This correction is essential for analyzing the smaller-scale temperature fluctuations that provide insights into the early universe. The discovery of the CMB dipole has implications beyond just our local motion. It also provides a reference frame for studying other large-scale motions in the universe. For example, by comparing the CMB dipole with the motion of galaxies, researchers can investigate the overall flow of matter in the cosmos. The dipole anisotropy is a fundamental aspect of the CMB that helps confirm the Big Bang model. The fact that we observe a dipole supports the idea that the CMB is a relic of the early universe, pervading all of space. This uniform background radiation would naturally exhibit a dipole due to our motion relative to the cosmos. In addition to our solar system's motion, the dipole can also reveal the motion of our galaxy, the Milky Way, relative to the CMB. The combined motion of our solar system and the Milky Way contributes to the observed dipole anisotropy. This layered understanding enhances our knowledge of cosmic velocities. The precise measurement of the CMB dipole has been achieved through various satellite missions, including COBE, WMAP, and Planck. These missions have provided highly accurate data, allowing scientists to determine the dipole's characteristics with great precision. This data is fundamental for cosmological research. The CMB dipole also provides a benchmark for testing the isotropy of the universe. While the dipole itself results from our motion, the smaller scale fluctuations should be isotropic and random. Any deviations from this isotropy could indicate new physics or previously unknown cosmic phenomena. By studying the CMB dipole, researchers can gain insights into the dynamics of our local cosmic environment. This includes understanding the gravitational influences of nearby galaxies and clusters. The dipole offers a window into the interactions between our galaxy and the larger structures in the universe. The existence of the dipole anisotropy is consistent with the predictions of the Big Bang theory. It supports the idea that the CMB is a remnant of the early universe, providing a consistent and coherent picture of cosmic history. This alignment between observation and theory is a cornerstone of modern cosmology. While the dipole is the largest anisotropy in the CMB, it is distinct from the smaller-scale fluctuations that provide information about the universe's initial conditions. These smaller fluctuations are imprinted with the density variations that eventually led to the formation of galaxies and large-scale structures. Understanding the CMB dipole also aids in the study of peculiar velocities. These are the motions of galaxies and clusters that deviate from the overall expansion of the universe. By analyzing the dipole, scientists can infer information about these peculiar velocities and their causes. The dipole anisotropy is a reminder of our place in the universe. It illustrates that even our motion through space can influence our observations of the cosmos. This connection between local motion and cosmic signals is a fascinating aspect of cosmological study. Overall, the CMB dipole is a fundamental feature that enhances our understanding of the universe. It provides critical information about our motion relative to the cosmos, supports the Big Bang model, and helps refine our cosmological measurements. Studying the dipole continues to be an essential part of unraveling the mysteries of the universe. The CMB quadrupole is the next level of temperature fluctuations after the dipole, representing variations on a larger angular scale. Unlike the dipole, which is caused by our motion, the quadrupole is an intrinsic feature of the cosmic microwave background. The quadrupole corresponds to temperature variations across the sky, with a spatial wavelength twice the size of the dipole. It is characterized by having 4 hot and 4 cold spots arranged in an alternating pattern. This pattern reflects the density variations in the early universe on these large scales. Measuring the quadrupole is more challenging than measuring the dipole because the temperature differences are smaller. The quadrupole temperature fluctuations are about 10 times smaller than the dipole, requiring precise instruments and careful data analysis to detect and interpret. The significance of the quadrupole lies in its potential to reveal information about the early universe's large-scale structure. These variations are thought to arise from primordial density fluctuations that were stretched to large scales by cosmic inflation, a rapid expansion that occurred shortly after the Big Bang. One of the puzzling aspects of the quadrupole is its lower-than-expected amplitude. The standard cosmological model predicts certain levels of quadrupole fluctuations, but observations show a deficit. This discrepancy has led to various hypotheses and remains an active area of research. The alignment of the quadrupole with other low multipoles, such as the octopole, is part of what forms the axis of evil. This unexpected alignment suggests that there might be more to these fluctuations than currently understood, potentially pointing to new physics or systematic effects not yet accounted for. Understanding the quadrupole helps in testing cosmological theories, including models of cosmic inflation. By comparing observed quadrupole data with theoretical predictions, scientists can refine their models and gain insights into the conditions of the early universe and the mechanisms that drove its expansion. The quadrupole also plays a role in determining the overall geometry of the universe. Its characteristics, along with other multipoles, help cosmologists assess whether the universe is flat, open, or closed. Current data, including the quadrupole, supports the idea that the universe is flat. Analyzing the quadrupole requires separating it from potential sources of contamination, such as foreground emissions from our galaxy. This process involves sophisticated algorithms and cross-checks with other observational data to ensure the quadrupole signal is accurately isolated and interpreted. The quadrupole's relatively low power compared to theoretical predictions might suggest the need for new physical mechanisms or modifications to existing models. Some theories propose that large-scale cosmic structures or even the topology of the universe could influence the quadrupole in unexpected ways. Studying the quadrupole in conjunction with other multipoles provides a more complete picture of the CMB and its implications. This comprehensive approach allows researchers to cross-verify findings and build a coherent understanding of the universe's large-scale properties and history. The quadrupole, like other CMB features, is a valuable tool for probing the early universe's conditions. By examining these large-scale temperature fluctuations, scientists can infer the properties of the primordial plasma and the processes that led to the formation of galaxies and clusters. The quadrupole's alignment with the octopole, forming the axis of evil, has prompted discussions about possible correlations and their significance. Understanding whether these alignments are coincidental or indicative of deeper physical principles is an ongoing challenge in cosmology. Despite its challenges, the study of the quadrupole is crucial for advancing our knowledge of cosmology. It provides unique insights into the early universe and helps refine our understanding of fundamental processes like cosmic inflation and the universe's large-scale structure. Continued observations and improved data from missions like Planck and future projects will help clarify the nature of the quadrupole. As our tools and methods become more sophisticated, we can expect to gain a deeper understanding of this intriguing feature of the cosmic microwave background. The relationship between the quadrupole and the axis of evil is central to understanding this cosmic anomaly. The axis of evil refers to the unexpected alignment of the quadrupole and octopole moments in the cosmic microwave background. This alignment suggests a preferred direction in the universe, which contradicts the standard cosmological model. The quadrupole's alignment with the octopole forms a significant part of the axis of evil. These low-order multipoles are expected to be randomly oriented, but their observed alignment raises questions about underlying cosmic structures or processes. This unusual pattern challenges our assumptions about the isotropy of the universe on large scales. The statistical significance of this alignment has been a topic of intense study. Researchers have used various methods to determine whether the axis of evil could be a fluke. However, the persistence of the alignment across different datasets and analysis techniques suggests it might be a real feature rather than a random occurrence. One hypothesis is that the alignment could be due to local foreground contamination. Galactic emissions or other nearby sources might influence the observed quadrupole and octopole, creating the appearance of a preferred direction. Efforts to remove these foregrounds have not entirely resolved the anomaly, keeping the debate open. Another possibility is that the alignment indicates new physics or previously unknown phenomena. If the quadrupole and octopole alignments are intrinsic to the CMB, they might point to new aspects of cosmic inflation or interactions with other cosmic structures. This could lead to revisions of current cosmological models. The axis of evil might also hint at the universe's large-scale topology. Some theories propose that the universe could have a non-trivial shape, such as being toroidal or having other complex geometries. Such shapes could naturally lead to alignments in the CMB multipoles, providing a geometric explanation for the axis of evil. The alignment raises questions about the initial conditions of the universe. If the axis of evil is a result of primordial density fluctuations, it could reveal new information about the early universe's state. This insight could help refine our understanding of the processes that occurred shortly after the Big Bang. The relationship between the quadrupole and the axis of evil also impacts the measurement of cosmological parameters. Accurate determination of these parameters relies on understanding all contributions to the CMB. Anomalies like the axis of evil must be accounted for to ensure precise cosmological models. Theoretical studies have explored how the alignment could influence our understanding of dark matter and dark energy. If the axis of evil is related to these mysterious components, it might provide indirect evidence about their properties and distribution. This could lead to breakthroughs in our understanding of the universe's composition. The alignment's persistence across different observational missions including WMAP and Planck, underscores its significance. Each new set of data has confirmed the presence of the axis of evil, suggesting it is not an artifact of any single experiment. This consistency has driven further research into its origins. The axis of evil has also influenced discussions about cosmic inflation. If inflationary models need to be adjusted to account for the alignment, this could change our understanding of the inflationary epoch. New or modified inflationary scenarios might be needed to explain the observed patterns. Exploring the quadrupole's relationship to the axis of evil encourages the development of new observational strategies. Future missions and experiments might be designed specifically to probe these large-scale anomalies, providing more data to clarify their nature. This could lead to innovative approaches in cosmology. The relationship between the quadrupole and the axis of evil illustrates the complexity of interpreting CMB data. It highlights the need for careful analysis and consideration of multiple hypotheses. This thorough approach is essential for advancing our knowledge and resolving cosmic mysteries. The continued study of the axis of evil and its connection to the quadrupole demonstrates the dynamic nature of cosmological research. Each new discovery or refinement in data analysis brings us closer to understanding these anomalies. The pursuit of knowledge in this area exemplifies the ongoing quest to unravel the universe's deepest secrets. Observational evidence for the axis of evil comes from multiple missions that have mapped the cosmic microwave background with increasing precision. The first hints of this anomaly were detected by the Wilkinson Microwave Anisotropy Probe, or WMAP, which launched in 2001. WMAP provided detailed maps of the CMB, revealing the unexpected alignments that form the axis of evil. WMAP's data showed a surprising correlation between the quadrupole and octupole moments. These low-order multipoles were not randomly oriented, as predicted by the standard model, but instead appeared to be aligned along a specific direction. This alignment was the first clear indication of the axis of evil. Following WMAP, the Planck satellite, launched by the European Space Agency in 2009, offered even higher resolution maps of the CMB. Planck's observations confirmed the axis of evil with greater precision, showing the same alignments seen in WMAP data. This consistency across different missions strengthened the case for the anomaly. Planck's data provided additional details about the alignment, allowing researchers to study its properties more closely. The satellite's high sensitivity and resolution revealed subtle features in the CMB that were not apparent in earlier observations. These findings provided a more comprehensive view of the axis of evil. To ensure that the alignment was not due to instrumental errors or data processing techniques, scientists conducted rigorous checks. They used different methods to analyze the data and compared results from multiple missions. The persistence of the axis of evil across these independent analyses suggested it was not an artifact of the instruments. Foreground contamination, such as emissions from our galaxy, was another potential explanation for the alignment. Researchers developed sophisticated algorithms to separate these foregrounds from the CMB signal. Despite these efforts, the axis of evil remained, indicating that it was not simply a result of foreground interference. The alignment has also been studied using data from ground-based and balloon-borne experiments. These additional observations have provided further confirmation of the axis of evil, showing that it is not limited to satellite data. The consistency across different types of observations adds to the robustness of the evidence. Statistical analyses have been crucial in assessing the significance of the axis of evil. Researchers have used various statistical tools to determine the likelihood that the alignment could occur by chance. These analyses have generally shown that the alignment is unlikely to be a random fluctuation, suggesting a real underlying phenomenon. And theoretical models have been tested against the observed data to see if they can account for the axis of evil. Standard cosmological models struggle to explain the alignment, prompting the exploration of alternative theories. These models include modifications to inflationary theory and the possibility of large-scale cosmic structures. Cosmic variance, the statistical uncertainty inherent in observations of the universe on large scales, is another factor considered in these studies. While cosmic variance can explain some deviations, the specific alignment seen in the axis of evil remains unusual, even when accounting for this uncertainty. Polarization data from the CMB has also been used to study the axis of evil. Polarization patterns provide additional information about the early universe and can help confirm the presence of anomalies. Observations of CMB polarization have supported the existence of the axis of evil, providing another layer of evidence. The continued collection and analysis of CMB data are essential for understanding the axis of evil. Future missions and experiments are expected to provide even more precise measurements, helping to clarify the nature of the alignment. These efforts are critical for resolving the questions raised by this anomaly. The axis of evil has motivated new observational strategies in cosmology. Scientists are designing experiments specifically to test the anomalies in the CMB, aiming to gather data that could either confirm or refute the presence of these features. This focused approach is necessary for making definitive progress. The persistence of the axis of evil in observational data challenges cosmologists to think creatively about the universe. It underscores the importance of remaining open to new ideas and possibilities, as unexpected findings can lead to significant advancements in our understanding of the cosmos. Overall, the observational evidence for the axis of evil is robust and consistent across multiple missions and analyses. This evidence continues to drive research and debate, highlighting the dynamic and evolving nature of cosmology. The quest to understand this anomaly exemplifies the ongoing pursuit of knowledge in the field. The axis of evil has significant implications for cosmological models, challenging some of the core assumptions in our understanding of the universe. One of the primary implications is the potential need to revisit the cosmological principle, which posits that the universe is homogeneous and isotropic on large scales. The alignment observed in the CMB suggests a preferred direction, contradicting this principle. If the axis of evil is confirmed as a real feature, it could indicate new physics beyond the standard model of cosmology. This might involve modifications to our theories of cosmic inflation, the rapid expansion that occurred just after the Big Bang. The alignment could point to specific conditions or mechanisms during inflation that have not been accounted for. The anomaly might also suggest the existence of large-scale structures or fields influencing the CMB. These could be remnants from the early universe that have left imprints on the CMB's temperature fluctuations. Understanding these structures could provide new insights into the distribution of matter and energy in the universe. Current models might need to incorporate anisotropies on large scales if the axis of evil is validated. This would require a shift from the assumption of a purely isotropic universe to one where directional dependencies are considered. Such a shift would have broad implications for our theoretical frameworks. The axis of evil could also impact our understanding of dark matter and dark energy. If these components of the universe are influencing the observed alignments, it could lead to new insights into their properties and interactions. This would be a major advancement in cosmology, as dark matter and dark energy remain poorly understood. The anomaly raises questions about the initial conditions of the universe. If the axis of evil reflects primordial features, it could suggest that the early universe had specific directional properties. This would influence our theories about how the universe evolved from its earliest moments. One theoretical explanation involves the topology of the universe. If the universe has a complex shape, such as being toroidal or having other non-trivial geometries, this could create the observed alignments. Exploring these topological models could provide a new perspective on cosmic structure. The axis of evil might also affect how we interpret other cosmic observations. For instance, if the CMB has a preferred direction, similar alignments might be found in the distribution of galaxies or large-scale flows of matter. This interconnectedness could lead to a more unified understanding of cosmic phenomena. Future cosmological models may need to account for the axis of evil by incorporating new parameters or adjusting existing ones. This could involve redefining certain aspects of inflationary theory or exploring alternative mechanisms for generating the CMB's temperature fluctuations. Such changes would have far-reaching effects on cosmological research. The implications extend to the methods used for cosmological measurements. If the axis of evil is real, it would necessitate more sophisticated techniques for analyzing CMB data and separating potential sources of contamination. This could drive advancements in observational technology and data processing. The alignment observed in the axis of evil also has potential implications for the study of cosmic variance. Understanding whether this alignment is an anomaly or part of a broader pattern could provide insights into the statistical nature of the universe. This would refine our interpretations of cosmological data. Theoretical models might also explore the influence of large-scale magnetic fields or other exotic phenomena. If such fields exist and impact the CMB, they could explain the observed alignments. Investigating these possibilities would expand the scope of cosmological theories. The axis of evil could encourage the development of new observational missions. Future satellites and ground-based experiments could be designed to specifically test the anomalies observed in the CMB. These targeted observations would help determine the nature and significance of the alignment. Ultimately, the axis of evil highlights the need for open-mindedness in cosmological research. As scientists explore this anomaly, they may uncover new principles or phenomena that reshape our understanding of the universe. This process exemplifies the dynamic nature of scientific inquiry and the continuous evolution of our knowledge. The ongoing study of the axis of evil and its implications underscores the importance of anomalies in driving scientific progress. By investigating these unexpected findings, researchers push the boundaries of existing theories and develop more comprehensive models of the universe. This pursuit is central to the advancement of cosmology. Satellite missions have been crucial in mapping the cosmic microwave background and uncovering anomalies like the axis of evil. The Cosmic Background Explorer, or COBE, was the first satellite dedicated to studying the CMB. Launched in 1989, COBE provided the first detailed measurements of the CMB's temperature fluctuations. COBE's findings were groundbreaking, confirming the CMB's blackbody spectrum and detecting small temperature variations. These results supported the Big Bang theory and provided a foundation for further CMB studies. COBE's success paved the way for more advanced missions. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in 2001. WMAP aimed to create more detailed maps of the CMB with higher resolution and sensitivity. The data from WMAP significantly enhanced our understanding of the CMB's structure. WMAP's observations revealed the first hints of the axis of evil, showing unexpected alignments in the quadrupole and octupole moments. These findings prompted further investigation into the nature of these alignments and their implications for cosmology. The Planck satellite, launched by the European Space Agency in 2009, represented a major leap forward in CMB observation. Planck was designed to measure the CMB with even greater precision than WMAP, providing the most detailed maps of the CMB to date. Planck's data confirmed the presence of the axis of evil, with higher accuracy and resolution. The consistency of the alignment across different missions strengthened the evidence for this anomaly. Planck's observations have been instrumental in studying the detailed properties of the CMB. The success of these satellite missions relies on their advanced instrumentation. COBE, WMAP, and Planck were equipped with sensitive detectors and cooling systems to measure the faint microwave radiation from the early universe. These technologies enabled precise measurements of the CMB's temperature and polarization. Each mission faced challenges in separating the CMB signal from foreground emissions. Galactic dust, synchrotron radiation, and other sources can contaminate the CMB data. Sophisticated algorithms were developed to filter out these foregrounds, ensuring accurate CMB measurements. COBE, WMAP, and Planck have provided a wealth of data for cosmologists. This data has been used to test theoretical models, refine our understanding of the universe's composition, and explore anomalies like the axis of evil. The detailed maps produced by these missions are a cornerstone of modern cosmology. The legacy of these missions extends beyond their immediate findings. They have set the stage for future CMB observations, inspiring new generations of scientists and guiding the development of next-generation instruments. The techniques and technologies pioneered by COBE, WMAP, and Planck continue to influence cosmological research. Future missions will build on the foundation laid by these satellites. Projects like the Simons Observatory and CMB-S4 aim to provide even more precise measurements of the CMB, with a focus on understanding anomalies and refining cosmological models. These missions are expected to provide new insights into the early universe. The collaborative nature of these missions has been vital for their success. International teams of scientists and engineers have worked together to design, launch, and analyze data from these satellites. This global collaboration has advanced our knowledge of the universe and fostered a vibrant scientific community. The data from COBE, WMAP, and Planck has also been made publicly available, allowing researchers worldwide to contribute to the study of the CMB. This openness has led to numerous discoveries and has helped to verify the robustness of the findings. The collaborative spirit continues to drive progress in the field. The detailed maps of the CMB produced by these missions have revealed not only large-scale structures, but also subtle features that challenge our understanding. Anomalies like the axis of evil illustrate the complexity of the universe and the need for continued exploration and innovation in cosmology. In summary, the COBE, WMAP, and Planck missions have transformed our understanding of the cosmic microwave background. They have provided the data needed to explore fundamental questions about the universe, including the mysterious alignments of the axis of evil. These missions represent a significant achievement in our quest to understand the cosmos. Data analysis techniques are crucial for interpreting the vast amounts of information collected from CMB observations. These techniques help isolate the true CMB signal from foreground contamination and instrumental noise. One of the first steps in data analysis is calibrating the instruments to ensure accurate measurements. Foreground removal is a critical part of analyzing CMB data. Emissions from our galaxy, such as dust and synchrotron radiation, can contaminate the CMB signal. Sophisticated algorithms are used to model and subtract these foregrounds, leaving a cleaner CMB map for further study. One common technique is component separation. This method involves breaking down the observed sky signal into different components, such as the CMB, galactic foregrounds, and extragalactic sources. By analyzing these components separately, scientists can better isolate the true CMB signal. Power spectrum analysis is another key technique. The power spectrum measures the amplitude of temperature fluctuations at different angular scales. By studying the power spectrum, researchers can learn about the universe's composition, geometry, and the processes that shaped its evolution. Harmonic analysis, specifically using spherical harmonics, is used to decompose the CMB temperature fluctuations into a series of multipoles. Each multipole corresponds to a different scale of fluctuation, helping scientists study the structure of the CMB at various levels. Statistical methods are employed to assess the significance of observed anomalies. These methods help determine whether features like the axis of evil are likely to be real, or if they could result from random fluctuations. Monte Carlo simulations are often used to test the robustness of these findings. Bayesian inference is a powerful tool in CMB data analysis. It allows researchers to combine prior knowledge with observed data to make probabilistic statements about cosmological parameters. This approach helps refine estimates of parameters like the Hubble constant and the density of dark matter. Cross-correlation techniques are used to compare CMB data with other cosmic observations. For example, cross-correlating CMB maps with galaxy surveys can provide insights into the distribution of matter in the universe and the integrated Sachs-Wolf effect. Machine learning and artificial intelligence are increasingly being applied to CMB data analysis. These techniques can automate the identification of patterns and anomalies, making it possible to process large datasets more efficiently and uncover subtle features that might be missed by traditional methods. Wavelet transforms are another advanced technique used to analyze CMB data. Wavelets allow for the examination of localized features in the CMB map, providing a multi-scale analysis that can reveal both large-scale and small-scale structures. Noise modeling is essential for understanding the limitations of CMB data. By accurately modeling the noise characteristics of the instruments, scientists can improve the precision of their measurements and better distinguish between real signals and noise. Polarization analysis is a crucial aspect of studying the CMB. Techniques for analyzing polarization data help to uncover information about the early universe's conditions and the presence of primordial gravitational waves. This analysis complements the study of temperature fluctuations. Likelihood analysis is used to compare theoretical models with observed data. By calculating the likelihood that a given model fits the data, researchers can determine which models are most consistent with observations and rule out less likely scenarios. Markov chain Monte Carlo, MCMC methods are employed to explore the parameter space of cosmological models. These methods generate a chain of samples from the parameter space, allowing researchers to estimate the posterior distribution of parameters and their uncertainties. Finally, visualization techniques are crucial for interpreting CMB data. Detailed maps and graphs help scientists and the public understand the structure and features of the CMB. Effective visualization aids in communicating complex findings and highlighting significant anomalies like the axis of evil. Statistical methods are essential for interpreting CMB data and understanding its underlying patterns. One fundamental technique is the calculation of the power spectrum, which quantifies the amplitude of temperature fluctuations at different angular scales. This spectrum provides critical insights into the universe's composition and geometry. Monte Carlo simulations play a significant role in CMB analysis. By generating numerous simulated datasets, researchers can assess the likelihood that observed features are real or merely the result of random fluctuations. This method helps in estimating the statistical significance of anomalies like the axis of evil. Maximum likelihood estimation is another key technique. It involves finding the set of cosmological parameters that maximize the likelihood function, given the observed data. This method is used to derive the best fit values for parameters such as the Hubble constant and the density of dark matter. Bayesian inference allows for the incorporation of prior knowledge into the analysis. By combining prior distributions with observed data, researchers can update their beliefs about cosmological parameters. This approach provides a probabilistic framework for parameter estimation and model comparison. Markov chain Monte Carlo, MCMC, methods are widely used in cosmological analysis. These algorithms generate samples from the posterior distribution of parameters, allowing for the estimation of their uncertainties. MCMC techniques are particularly useful for exploring complex multidimensional parameter spaces. The chi-square test is a common statistical test used to compare observed data with theoretical models. By calculating the chi-square statistic, researchers can assess how well a model fits the data. A lower chi-square value indicates a better fit between the model and the observations. Principal component analysis, PCA, is used to reduce the dimensionality of CMB data, identifying the most significant features. PCA transforms the data into a set of orthogonal components, making it easier to analyze the underlying structure and identify patterns that might be obscured in the original dataset. Cross-correlation analysis measures the degree to which two datasets are correlated. In CMB studies, cross-correlation can be used to compare the CMB with other cosmic signals, such as galaxy distributions or gravitational lensing maps. This method helps in understanding the relationships between different cosmic phenomena. Wavelet analysis is a powerful tool for examining localized features in the CMB. Wavelets allow for multi-scale analysis, providing insights into both large-scale and small-scale structures. This technique is particularly useful for detecting anomalies and studying their properties across different scales. Gaussian processes are used to model the CMB data as a realization of a random field. This approach provides a flexible and non-parametric way to describe the data, capturing the correlations and uncertainties inherent in the measurements. Gaussian processes are useful for making predictions and inferring the properties of the underlying field. Hypothesis testing is employed to determine whether observed features are consistent with theoretical predictions. By comparing the observed data with the expected distribution under a null hypothesis, researchers can assess the likelihood of various models. This method is crucial for validating or refuting cosmological theories. Information criteria such as the Akaike Information Criterion, AIC, and the Bayesian Information Criterion, BIC, are used to compare different models. These criteria balance the goodness of fit with model complexity, helping to identify the most parsimonious model that adequately describes the data. Jackknife and bootstrap resampling methods are used to estimate the uncertainties and biases in CMB data. These techniques involve repeatedly resampling the data and recalculating the statistics of interest. This approach provides robust estimates of the variability and reliability of the results. Covariance matrix estimation is essential for understanding the correlations between different data points. By estimating the covariance matrix, researchers can account for these correlations in their analyses, leading to more accurate parameter estimates and model comparisons. Finally, data visualization techniques are crucial for interpreting statistical results. Effective visualizations, such as contour plots and heat maps, help to communicate the relationships between parameters and the significance of various features in the data. These visual tools are invaluable for both analysis and presentation of CMB research findings. Detecting the axis of evil presents several challenges that researchers must overcome to ensure the validity of their findings. One major challenge is separating the CMB signal from foreground emissions. Our galaxy emits radiation that can contaminate the CMB data, making it difficult to isolate the true cosmic signal. Foreground removal requires sophisticated algorithms and careful analysis. Dust, synchrotron radiation, and free emission are some of the primary sources of contamination. These must be accurately modeled and subtracted to reveal the underlying CMB fluctuations. Instrumental noise is another significant challenge. Each satellite and detector has its own noise characteristics, which can introduce errors into the data. Ensuring that these noise sources are well understood and mitigated is crucial for accurate measurements. The precision of the instruments also plays a critical role. High-resolution and sensitive detectors are necessary to detect the subtle temperature variations in the CMB. Any limitations in the instrument's capabilities can affect the quality of the data. Cosmic variance adds another layer of complexity. This refers to the statistical uncertainty inherent in observations of the universe on large scales. Because we can only observe one realization of the universe, it's challenging to distinguish between true anomalies and random fluctuations. Beam effects can also influence the detection of the axis of evil. The shape and response of the instrument's beam can distort the observed CMB signal. Correcting for these beam effects is essential for accurate interpretation of the data. The alignment seen in the axis of evil is on large angular scales, making it particularly susceptible to systematic errors. Ensuring that these large-scale features are not artifacts of the data collection or processing methods is a significant challenge. Calibration of the instruments must be precise to ensure that the data accurately reflects the true CMB signal. Any errors in calibration can lead to incorrect conclusions about the presence of anomalies like the axis of evil. The statistical analysis itself is complex and must be carefully conducted. Determining the significance of the axis of evil requires robust statistical methods to ensure that the observed alignment is not a random occurrence. Different data analysis techniques can yield different results. Researchers must carefully choose and validate their methods to ensure that their findings are reliable. This often involves cross-checking results using multiple techniques. Data from multiple missions must be compared and combined. Each mission, such as COBE, WMAP, and Planck, has its own strengths and weaknesses. Combining data from these sources requires careful consideration to ensure consistency and accuracy. Biases in data interpretation can also pose challenges. Researchers must remain objective and avoid letting preconceived notions influence their analysis. Ensuring that the analysis is conducted blind, without prior knowledge of the expected outcomes, can help mitigate this risk. Detecting the axis of evil also involves dealing with incomplete sky coverage. Some regions of the sky are obscured or more challenging to observe, which can introduce biases into the analysis. Efforts to account for these gaps are necessary for a complete picture. Theoretical uncertainties add another layer of difficulty. Different cosmological models can predict different behaviors for the CMB, and these predictions must be carefully considered when interpreting the data. Researchers must remain open to various theoretical explanations. Finally, the evolving nature of technology and methods means that detection techniques must continually improve. Staying at the forefront of technological advancements and analytical methods is crucial for accurately detecting and understanding anomalies like the axis of evil. Results from different missions have provided a comprehensive view of the cosmic microwave background and its anomalies, including the axis of evil. The Cosmic Background Explorer, or COBE, was the first mission to provide detailed measurements of the CMB. Launched in 1989, COBE confirmed the CMB's blackbody spectrum and detected small temperature fluctuations. COBE's results were groundbreaking, showing that the CMB was remarkably uniform with tiny variations. These findings supported the Big Bang theory and set the stage for future missions to explore the CMB in greater detail. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided higher resolution maps of the CMB. WMAP's data revealed the first hints of the axis of evil, showing unexpected alignments in the quadrupole and octupole moments. These findings challenged the standard cosmological model and sparked further investigation. WMAP's results also provided precise measurements of the universe's age, composition, and geometry. The data indicated that the universe is flat, dominated by dark energy, and approximately 13.8 billion years old. These findings have become central to modern cosmology. The Planck satellite, launched by the European Space Agency in 2009, took CMB observations to an even higher level of precision. Planck's data confirmed the axis of evil with greater accuracy, showing the same alignment seen in WMAP data. The consistency across different missions reinforced the significance of this anomaly. Planck provided the most detailed maps of the CMB to date, revealing subtle features that were not apparent in earlier observations. These high-resolution maps allowed for a more comprehensive study of the CMB's temperature and polarization fluctuations. Planck's results also refined measurements of cosmological parameters. The data improved our understanding of the universe's composition, confirming the proportions of dark matter, dark energy, and ordinary matter. Planck's findings have been crucial for testing and refining cosmological models. Other missions, such as the Atacama Cosmology Telescope and the South Pole Telescope, have also contributed to CMB research. These ground-based observatories provide complementary data, helping to verify findings from space-based missions and offering additional insights into the CMB's properties. The combination of data from COBE, WMAP, and Planck has provided a robust and detailed picture of the CMB. This multi-mission approach allows researchers to cross-validate findings and ensure that results are not artifacts of a single instrument or method. Each mission has built on the successes of its predecessors, enhancing our understanding of the universe's earliest moments. The detailed observations have revealed not only the large-scale structure of the CMB, but also finer details that continue to challenge and refine cosmological theories. The results from these missions have had significant implications for our understanding of cosmic inflation. The data supports the idea that the universe underwent a rapid expansion shortly after the Big Bang, stretching tiny quantum fluctuations to cosmic scales. The detection of the axis of evil across multiple missions suggests that it is a genuine feature of the CMB, not an artifact of any particular dataset. This persistence has motivated researchers to explore various theoretical explanations for the alignment. Future missions aim to build on these results, providing even more precise measurements of the CMB. Projects like the Simons Observatory and CMB S4 are expected to enhance our understanding of the CMB's anomalies and refine our cosmological models further. The legacy of these missions extends beyond their immediate findings. They have established a framework for CMB research that will guide future investigations and continue to advance our knowledge of the universe. The results from these missions remain a cornerstone of modern cosmology. In summary, the combined results from COBE, WMAP, and Planck have revolutionized our understanding of the CMB and its anomalies. The detailed data from these missions continues to shape the field of cosmology, driving new discoveries and theoretical developments. The study of the CMB remains a dynamic and evolving area of research. The standard cosmological model, also known as the lambda cold dark matter model or lambda CDM, is the prevailing theory that describes the large-scale structure and evolution of the universe. This model combines the Big Bang theory with the concept of cosmic inflation, dark matter, and dark energy. Lambda CDM is built on the foundation of the Big Bang theory, which posits that the universe began as a hot, dense singularity approximately 13.8 billion years ago. Since then, the universe has been expanding and cooling, leading to the formation of galaxies, stars, and other cosmic structures. One of the key components of the standard cosmological model is cosmic inflation. This theory suggests that a rapid expansion of the universe occurred a fraction of a second after the Big Bang, smoothing out any initial irregularities and leading to the large-scale homogeneity observed today. Dark matter is another crucial element of the lambda CDM model. This invisible form of matter does not emit or interact with electromagnetic radiation, making it undetectable through direct observation. However, its presence is inferred from its gravitational effects on visible matter and the overall structure of the universe. Dark energy, represented by the lambda in lambda CDM, is a mysterious form of energy that permeates all of space and is driving the accelerated expansion of the universe. Dark energy makes up about 70% of the total energy density of the universe, according to the Standard Model. The Standard Cosmological Model also incorporates the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. This means that the universe looks the same in every direction and has a uniform distribution of matter and energy when viewed on a sufficiently large scale. The lambda CDM model successfully explains a wide range of observations, including the cosmic microwave background, the large-scale structure of the universe, and the distribution of galaxies. It provides a coherent framework for understanding the universe's history and its current state. One of the key predictions of the Standard Cosmological Model is the abundance of light elements. During the first few minutes after the Big Bang, nuclear reactions produced hydrogen, helium, and trace amounts of other light elements. The observed abundances of these elements match the predictions of the model. The lambda CDM model also explains the large-scale distribution of galaxies. Galaxies are not randomly distributed, but form a web-like structure with clusters, filaments, and voids. This cosmic web is thought to have formed from the gravitational collapse of dark matter and baryonic matter. Observations of the cosmic microwave background provide strong support for the Standard Cosmological Model. The CMB's temperature fluctuations, as mapped by missions like COBE, WMAP, and Planck, are consistent with predictions from the lambda CDM model, providing a snapshot of the universe's early conditions. The model also accounts for the observed expansion of the universe. Measurements of distant supernovae, galaxy clusters, and the CMB all indicate that the universe is expanding at an accelerating rate, driven by dark energy. This acceleration is a key feature of the lambda CDM model. Despite its successes, the Standard Cosmological Model has some unresolved issues. The nature of dark matter and dark energy remains unknown, and the model does not fully explain the observed anomalies in the CMB, such as the axis of evil. These challenges motivate ongoing research in cosmology. The lambda CDM model continues to evolve as new observations are made. Future missions and experiments aim to provide more detailed data, helping to refine the model and address its current limitations. These efforts are crucial for improving our understanding of the universe. In summary, the Standard Cosmological Model, lambda CDM, provides a comprehensive framework for understanding the universe's large-scale structure and evolution. It successfully explains a wide range of observations, though some mysteries remain. Continued research and observations are essential for refining the model and uncovering the nature of dark matter, dark energy, and other cosmic phenomena. The study of the universe's origins and evolution remains a dynamic and exciting field of scientific inquiry. The axis of evil suggests potential deviations from the Standard Cosmological Model. This unexpected alignment in the CMB challenges the assumption that the universe is isotropic on large scales. If the axis of evil is confirmed, it may indicate new physics beyond the current model. One potential deviation involves modifications to the theory of cosmic inflation. Inflation is supposed to produce a uniform, isotropic universe, but the axis of evil implies a preferred direction. This could mean that inflationary models need to be adjusted to account for these large-scale anomalies. The presence of the axis of evil might also suggest that the early universe had specific conditions or fields influencing its development. These could include primordial magnetic fields or other exotic physics that have left imprints on the CMB. If the alignment is real, it could impact our understanding of dark matter and dark energy. These components might have properties or interactions that create large-scale anisotropies. Investigating these possibilities could lead to new insights into the nature of dark matter and dark energy. The axis of evil could also affect the measurement of cosmological parameters. Parameters like the Hubble constant, the density of matter, and the properties of dark energy might need to be re-evaluated in light of this anomaly. Accurate measurements of these parameters are crucial for refining our cosmological models. The anomaly might indicate that the universe has a more complex geometry than currently thought. The standard model assumes a flat or simple curved geometry, but the axis of evil could suggest a more intricate structure, possibly involving higher dimensions or non-trivial topology. Theoretical models might need to incorporate anisotropies at large scales. This would represent a shift from the assumption of a purely isotropic universe, requiring new theories or modifications to existing ones. Such a shift would have broad implications for our understanding of the universe's structure and evolution. The axis of evil could imply the existence of large-scale cosmic structures or voids that influence the CMB. These structures might have formed during the early universe and left a lasting impact on the cosmic microwave background. Understanding these structures could provide new insights into the distribution of matter in the universe. Another potential deviation involves the cosmic variance, which is the statistical uncertainty in measurements of the universe on large scales. If the axis of evil is a genuine feature, it might suggest that our current understanding of cosmic variance is incomplete. This could lead to new methods for analyzing cosmological data. The anomaly might also prompt a re-evaluation of the initial conditions of the universe. If the axis of evil reflects primordial features, it could suggest that the early universe had specific directional properties. This would influence our theories about how the universe evolved from its earliest moments. Exploring the axis of evil could lead to the discovery of new physical mechanisms. These mechanisms might explain the alignment and provide a deeper understanding of the forces that shaped the early universe. Such discoveries would have significant implications for theoretical physics and cosmology. The anomaly could also influence the interpretation of other cosmic observations. If the CMB has a preferred direction, similar alignments might be found in the distribution of galaxies, large-scale flows of matter, or other cosmic phenomena. This interconnectedness could lead to a more unified understanding of the universe. The presence of the axis of evil might encourage the development of new observational strategies. Future missions and experiments could be designed specifically to test the anomalies observed in the CMB. These targeted observations would help determine the nature and significance of the alignment. Theoretical work might explore the influence of large-scale magnetic fields or other exotic phenomena. If such fields exist and impact the CMB, they could explain the observed alignments. Investigating these possibilities would expand the scope of cosmological theories and deepen our understanding of the universe. Ultimately, the axis of evil highlights the need for open-mindedness in cosmological research. As scientists explore this anomaly, they may uncover new principles or phenomena that reshape our understanding of the universe. This process exemplifies the dynamic nature of scientific inquiry and the continuous evolution of our knowledge. The quest to understand the axis of evil and its implications continues to drive progress in the field of cosmology. The axis of evil has significant implications for inflation theory. Inflation is the rapid expansion of the universe that occurred a fraction of a second after the Big Bang. It is supposed to create a homogeneous and isotropic universe. However, the axis of evil suggests a preferred direction, challenging this assumption. If the axis of evil is real, it might indicate that the initial conditions of inflation were not perfectly uniform. This could mean that the inflationary field had variations that led to large-scale anisotropies. Understanding these variations would require modifications to standard inflationary models. One potential modification involves introducing a new field or mechanism that breaks the isotropy during inflation. This field could have influenced the inflationary dynamics, creating the observed alignments in the CMB. Such a modification would expand our understanding of the forces and fields at play in the early universe. The axis of evil could also imply that the inflationary potential, which describes how the inflation field evolves, is more complex than previously thought. The potential might have features that create directional dependencies, leading to the observed anisotropies. This would necessitate a rethinking of the fundamental shape of the inflationary potential. Another possibility is that the universe underwent multiple phases of inflation, with each phase leaving its own imprint on the CMB. These phases could have different characteristics, leading to the large-scale alignment seen in the axis of evil. This scenario would require a significant revision of current inflationary models. The alignment might also suggest that the initial quantum fluctuations that seeded the universe were not entirely random. If there were correlations between these fluctuations, they could produce the preferred directions observed in the CMB. This would challenge the standard assumption that these fluctuations were purely stochastic. The impact on inflation theory extends to the predictions of primordial gravitational waves. Inflation is expected to produce gravitational waves that leave a distinct signature in the CMB's polarization. If the axis of evil affects these predictions, it could alter the expected signal, influencing how we search for and interpret primordial gravitational waves. Exploring the axis of evil could lead to new insights into the reheating phase, the period after inflation when the universe heats up and particles are created. The dynamics of reheating might play a role in creating large-scale anisotropies. Understanding this phase is crucial for connecting inflationary theory with the later stages of the universe's evolution. The anomaly might also indicate that our understanding of the universe's topology is incomplete. If the universe has a non-trivial topology, such as being shaped like a torus or having other complex structures, this could create the observed alignments. This would require a fundamental shift in our understanding of the universe's shape and geometry. Theoretical work on the axis of evil could lead to the development of new inflationary scenarios. These scenarios might incorporate additional fields, modified potentials, or different initial conditions to account for the observed anisotropies. Such developments would broaden the scope of inflationary theory and deepen our understanding of the early universe. The axis of evil also highlights the importance of precision in inflationary predictions. Small deviations from isotropy can have significant implications for our understanding of the inflationary process. This underscores the need for detailed and accurate models to capture the complexities of the early universe. Future observations of the CMB, particularly its polarization, will be crucial for testing the impact of the axis of evil on inflation theory. New data from upcoming missions and experiments will help refine our models and determine whether the observed alignments are a real feature of the universe or a statistical anomaly. The potential need to modify inflationary theory due to the axis of evil illustrates the dynamic nature of cosmological research. As new data and anomalies are discovered, our theories must adapt and evolve to incorporate these findings. This process is essential for advancing our understanding of the universe. The axis of evil serves as a reminder that our understanding of the early universe is still incomplete. It challenges us to look beyond the current models and explore new possibilities. This quest for knowledge drives the progress of science and leads to deeper insights into the nature of the cosmos. In summary, the axis of evil has profound implications for inflation theory. It suggests that the early universe might have had more complex conditions than previously thought, potentially requiring modifications to our models. As research continues, the study of this anomaly will help refine our understanding of inflation and the origins of the universe. The axis of evil could have significant implications for our understanding of dark matter and dark energy. These components make up most of the universe's mass-energy content, but remain poorly understood. The observed alignment in the CMB might suggest new properties or interactions for these mysterious substances. Dark matter is believed to interact primarily through gravity, yet the axis of evil might indicate additional interactions or properties. If dark matter has subtle interactions with other fields or particles, this could influence the large-scale structure of the universe, potentially creating the observed anisotropies. The alignment might suggest that dark matter is not uniformly distributed. Instead, there could be large-scale clumps or structures that affect the CMB. This non-uniform distribution could provide new clues about the nature and behavior of dark matter in the early universe. The axis of evil could also affect our understanding of dark energy. This mysterious force is driving the accelerated expansion of the universe, but its properties are largely unknown. If dark energy has anisotropic properties, it could influence the CMB in ways that create the observed alignment. The relationship between dark energy and the axis of evil might suggest a more complex model for dark energy. Instead of being a simple uniform force, dark energy could have directional dependencies or interact with other cosmic fields. This would require significant modifications to current models. Exploring these possibilities could lead to a deeper understanding of how dark matter and dark energy interact with each other and with ordinary matter. The axis of evil might be a key to unlocking these interactions, providing insights that could revolutionize our understanding of the universe's composition. If dark matter or dark energy contribute to the axis of evil, it could affect how we measure their properties. Parameters such as the density and equation of state of dark energy might need to be re-evaluated in light of this anomaly. Accurate measurements are crucial for refining our cosmological models. The observed alignment might also suggest new types of dark matter or dark energy. For example, there could be multiple forms of dark matter with different properties, or dark energy could be composed of multiple components. These new forms could create the anisotropies seen in the CMB. Investigating the axis of evil could lead to the discovery of new particles or forces. If these new entities interact with dark matter or dark energy, they could influence the large-scale structure of the universe. Such discoveries would have profound implications for both cosmology and particle physics. The anomaly might also provide clues about the early universe's conditions. If dark matter and dark energy played a role in creating the axis of evil, it could indicate that these components were active in shaping the universe from its earliest moments. This would provide a new perspective on cosmic evolution. The axis of evil could motivate the development of new theoretical models. These models might incorporate additional fields or interactions to explain the observed alignment. Such theoretical work could lead to a more comprehensive understanding of the universe's fundamental forces and components. Understanding the influence of the axis of evil on dark matter and dark energy could also help resolve other cosmological puzzles. For instance, it might provide insights into the nature of cosmic acceleration or the behavior of dark matter in galaxy formation. These connections could unify various aspects of cosmology. Future observations and experiments will be crucial for testing these ideas. Improved measurements of the CMB, as well as observations of galaxy distributions and gravitational lensing, will help determine whether the axis of evil is linked to dark matter and dark energy. These data will guide the development of new models. The study of the axis of evil underscores the interconnectedness of cosmological phenomena. By exploring how this anomaly relates to dark matter and dark energy, researchers can gain a deeper understanding of the universe's overall structure and evolution. This holistic approach is essential for advancing cosmology. Ultimately, the axis of evil challenges us to think beyond the current models and consider new possibilities. It highlights the complexity of the universe and the need for continued exploration and innovation in science. As we delve deeper into these mysteries, we move closer to unraveling the fundamental nature of the cosmos. The axis of evil has broader implications for our understanding of the universe's structure. Its existence suggests that the universe might not be as isotropic as previously thought, indicating large-scale anisotropies that challenge the cosmological principle. This could lead to a re-evaluation of our assumptions about the universe's homogeneity. If the axis of evil is confirmed, it might imply that the universe has a preferred direction or axis. This could mean that the distribution of matter and energy is not uniform on the largest scales, potentially altering our models of cosmic evolution and structure formation. The presence of large-scale alignments could influence our understanding of galaxy formation and distribution. If the universe has directional dependencies, these could affect how galaxies and clusters formed and evolved, leading to anisotropies in their large-scale distribution. The anomaly might also suggest that there are previously unknown structures or fields in the universe. These structures could be remnants from the early universe that have influenced the CMB, leaving an imprint that we see as the axis of evil. Identifying these structures would provide new insights into cosmic history. The axis of evil could impact our understanding of cosmic topology. If the universe has a complex shape, such as a torus or other non-trivial geometry, this could naturally create the observed alignments. This would require a significant revision of our understanding of the universe's shape and geometry. The existence of large-scale anisotropies might imply that the universe is not infinite and unbounded. Instead, it could have a finite size with a specific shape that influences the distribution of matter and energy. This possibility challenges the conventional view of an infinite, homogeneous universe. These implications extend to the study of cosmic inflation. If the initial conditions of inflation were not perfectly uniform, this could lead to the large-scale anisotropies observed today. Understanding these initial conditions is crucial for refining inflationary models and their predictions. The axis of evil might also provide insights into the distribution of dark matter and dark energy. If these components have anisotropic properties, they could influence the large-scale structure of the universe. This would help us understand their role in shaping the cosmos. The anomaly could influence the interpretation of other cosmic observations, such as the distribution of quasars or the cosmic web. If there are large-scale anisotropies, they might also be reflected in these observations, providing a more integrated view of the universe's structure. The presence of large-scale alignments challenges the current understanding of cosmic variance. If the axis of evil is a real feature, it suggests that our statistical models of the universe might need to be revised to account for these anisotropies. This could lead to new methods for analyzing cosmological data. The broader implications of the axis of evil also include potential new physical mechanisms. These mechanisms might explain the observed anisotropies and provide a deeper understanding of the forces that shaped the early universe. This could lead to significant advancements in theoretical physics. Future observations will be crucial for exploring these broader implications. Improved measurements of the CMB, as well as observations of large-scale structures and gravitational waves, will help determine the nature and significance of the axis of evil. These data will guide the development of new models. The study of the axis of evil underscores the importance of precision and accuracy in cosmological measurements. Small anomalies can have significant implications, highlighting the need for advanced observational techniques and careful data analysis. Exploring the broader implications of the axis of evil encourages a multidisciplinary approach. Combining insights from cosmology, astrophysics, and theoretical physics will be essential for understanding this anomaly and its impact on our models of the universe. Ultimately, the axis of evil represents a fascinating and challenging puzzle for cosmology. Its broader implications for the universe's structure and evolution highlight the complexity of the cosmos and the need for continued exploration and innovation in our quest to understand the universe. The foreground contamination hypothesis suggests that the axis of evil might be an artifact created by local sources of radiation rather than a true cosmological feature. Foreground emissions from our galaxy and other sources can interfere with the CMB signal, making it challenging to separate the true cosmic background from these contaminants. Galactic dust is a primary source of foreground contamination. Dust grains in the Milky Way emit radiation at microwave wavelengths, which can obscure the CMB signal. These emissions can create patterns in the data that might be mistaken for large-scale cosmic alignments. Synchrotron radiation is another significant source of contamination. This radiation is produced by high-energy electrons spiraling around magnetic fields in our galaxy. Synchrotron emissions can be particularly problematic at lower frequencies, adding complexity to the data analysis. Free emission or bremsstrahlung is caused by electrons scattering off ions in the interstellar medium. This type of radiation contributes to the foreground signal, especially at higher frequencies, and must be carefully modeled and subtracted from the CMB data. To address foreground contamination, scientists use multi-frequency observations. By observing the sky at different wavelengths, they can distinguish between the CMB and foreground emissions. Each type of foreground radiation has a distinct spectral signature, allowing researchers to separate it from the cosmic signal. Component separation algorithms are crucial in this process. These algorithms analyze the multi-frequency data to isolate the CMB from the various foreground components. Techniques such as the internal linear combination, ILC method, and the maximum entropy method, MEM, are commonly used. Despite these sophisticated methods, completely removing foreground contamination is challenging. Residual foreground emissions can still influence the data, potentially creating artifacts like the axis of evil. Researchers continuously refine their techniques to minimize these effects and ensure the accuracy of their results. One approach to validating the results is cross-correlation with other datasets. By comparing the CMB maps with independent observations, such as galaxy surveys or other cosmic signals, scientists can check for consistency and identify potential foreground artifacts. The Planck satellite, with its broad frequency coverage and high sensitivity, has provided the most detailed maps of the CMB and foreground emissions. Planck's data have been instrumental in improving our understanding of foreground contamination and refining the methods used to remove it. However, the presence of the axis of evil in Planck's data, despite these advanced techniques, suggests that either the anomaly is real or our methods for handling foregrounds need further improvement. This ongoing challenge drives continued research and innovation in data analysis. Foreground contamination can also vary across different regions of the sky. Some areas, like the galactic plane, have higher levels of emissions, making it harder to extract a clean CMB signal. Researchers must account for these variations to ensure their results are not biased by localized contamination. Statistical methods are used to assess the likelihood that the axis of evil is due to foreground contamination. By simulating foreground emissions and analyzing their impact on the CMB data, scientists can estimate the probability that the observed alignment is an artifact. Even with the best techniques, some level of uncertainty remains. This uncertainty highlights the importance of transparency and rigor in data analysis, as well as the need for independent verification of results by multiple research teams. Understanding and mitigating foreground contamination is essential for all CMB studies, not just those related to the axis of evil. Accurate separation of the cosmic signal from local emissions is crucial for testing cosmological models and refining our understanding of the universe's origins. Ultimately, the foreground contamination hypothesis underscores the complexity of CMB data analysis. While it offers a potential explanation for the axis of evil, it also highlights the need for continued advancements in observational techniques and data processing to fully understand this intriguing anomaly. Instrumental errors are another possibility that could explain the axis of evil. These errors can arise from imperfections in the instruments used to measure the cosmic microwave background. Even slight inaccuracies in the detectors or their calibration can introduce artifacts into the data. The design and calibration of instruments are crucial for accurate CMB measurements. Each component, from the detectors to the optics, must be precisely engineered and tested. Any deviation from the intended performance can impact the quality of the data collected. One potential source of instrumental error is the beam shape. The telescope's beam pattern, which describes how it responds to incoming radiation from different angles, must be well characterized. Imperfections in the beam shape can distort the observed signal, creating artificial alignments. Thermal fluctuations in the detectors can also introduce noise. Detectors must be kept at extremely low temperatures to minimize thermal noise. However, any residual fluctuations can affect the measurements, potentially contributing to the observed anomalies. Pointing accuracy is another critical factor. The telescope must be able to point precisely at different regions of the sky. Errors in pointing can lead to misalignments in the data, which might be misinterpreted as cosmic features like the axis of evil. Data processing pipelines must account for these potential errors. Raw data from the instruments undergoes extensive processing to remove noise and correct for known instrumental effects. Any shortcomings in this processing can leave residual errors that impact the final results. The Planck satellite, for example, had to account for various instrumental effects in its data analysis. Despite rigorous calibration and correction procedures, some level of uncertainty remains. The persistence of the axis of evil in Planck's data suggests that instrumental errors alone may not fully explain the anomaly. Cross-validation with other instruments and missions is essential. By comparing data from different telescopes, researchers can identify and correct for instrumental biases. Consistent findings across multiple instruments increase confidence that the observed features are real. Simulations play a crucial role in understanding instrumental errors. Researchers create detailed models of their instruments and simulate observations of the CMB. These simulations help identify how different types of errors might manifest in the data and how they can be mitigated. Instrumental errors can also vary over time. As instruments age, their performance can change, introducing new sources of error. Continuous monitoring and recalibration are necessary to maintain the accuracy of the measurements. The complexity of the data analysis pipeline means that even small errors can propagate and amplify through the process. This underscores the importance of thorough testing and validation at every stage of the analysis. Independent verification by multiple research teams helps to ensure the robustness of the results. Different teams may use varying methods and assumptions, which can help identify and correct for potential instrumental biases. Despite the challenges, the rigorous design and calibration of instruments have led to significant advancements in CMB measurements. While instrumental errors cannot be completely ruled out, the consistency of the axis of evil across different missions suggests that these errors are unlikely to be the sole cause. Understanding and mitigating instrumental errors is a continuous process. As technology advances, new instruments with improved capabilities will provide even more precise measurements, helping to clarify the nature of the axis of evil. Ultimately, addressing the possibility of instrumental errors highlights the meticulous care required in cosmological research. It underscores the need for continued innovation and rigorous testing to ensure that our observations accurately reflect the true nature of the universe. The possibility that the axis of evil is a statistical fluke must be considered. In cosmology, we often deal with large datasets, where random alignments can occur purely by chance. Determining whether an observed feature is significant or just a random occurrence is a fundamental challenge. One argument for the statistical fluke hypothesis is based on the principle of cosmic variance. Cosmic variance refers to the inherent statistical uncertainty in measurements of the universe on large scales. Given that we only observe one universe, some degree of variation is expected. Researchers use simulations to assess the likelihood of the axis of evil being a statistical fluke. By generating many synthetic CMB maps based on the standard cosmological model, they can compare the observed alignment with what might randomly occur. If similar alignments appear frequently in these simulations, the anomaly might not be significant. The probability of a fluke can be quantified through p-values. A low p-value indicates that the observed feature is unlikely to have occurred by chance. For the axis of evil, p-values are calculated to determine how rare such an alignment would be in a universe governed by the standard model. However, the p-values for the axis of evil are somewhat controversial. Some studies suggest that the alignment has a low p-value, indicating it is unlikely to be a fluke, while others argue that the p-values are not low enough to rule out the possibility. This discrepancy highlights the complexity of statistical analysis in cosmology. Multiple testing is another factor to consider. When examining large datasets, researchers often test many hypotheses simultaneously. This increases the chance of finding at least one seemingly significant result purely by chance. Correcting for multiple testing is crucial to avoid overestimating the significance of anomalies like the axis of evil. Bayesian statistics offers another approach to evaluating the fluke hypothesis. Bayesian methods incorporate prior knowledge and update the probability of a hypothesis based on new data. Applying Bayesian analysis to the axis of evil can provide a more nuanced view of its likelihood as a statistical fluke. Critics of the statistical fluke argument point out the consistency of the axis of evil across different datasets and missions. If the alignment were a fluke, it would be less likely to persist across independent observations. This consistency suggests that the feature might be genuine. Additionally, some argue that the statistical fluke hypothesis does not fully account for the observed alignment's specific characteristics. The precise nature and direction of the alignment might be difficult to reproduce through random chance alone, indicating that there could be an underlying cause. The possibility of a statistical fluke does not negate the need for further investigation. Even if the axis of evil is a fluke, understanding why such alignments appear in simulations can provide valuable insights into the nature of cosmic variance and the limitations of our models. Future observations and more refined statistical analyses are needed to resolve this debate. As new data becomes available from upcoming missions, researchers will have more tools to determine whether the axis of evil is a genuine feature or a statistical anomaly. The fluke hypothesis also underscores the importance of skepticism and rigor in scientific inquiry. It reminds us that extraordinary claims require extraordinary evidence, and that robust methods are needed to distinguish between real phenomena and random occurrences. Collaborative efforts and independent verification are essential for addressing the fluke hypothesis. By sharing data and methodologies, the scientific community can collectively assess the validity of the axis of evil and other anomalies. Ultimately, the statistical fluke argument highlights the challenges inherent in cosmological research. It emphasizes the need for precise measurements, careful analysis, and an open-minded approach to interpreting complex data. Whether the axis of evil is a fluke or a genuine feature, its study advances our understanding of the universe. Galactic emission interference is a significant factor when analyzing the cosmic microwave background. Emissions from our galaxy can contaminate the CMB signal, complicating efforts to detect anomalies like the axis of evil. These emissions primarily come from sources such as galactic dust, synchrotron radiation, and free emission. Galactic dust is composed of small particles that emit radiation at microwave frequencies. This emission can create patterns in the data that mimic or obscure the CMB's true features. Accurately modeling and removing this dust emission is critical to isolating the CMB signal. Synchrotron radiation, produced by high-energy electrons spiraling around magnetic fields, adds another layer of complexity. This type of radiation is especially prevalent at lower frequencies and can significantly impact CMB measurements. Sophisticated techniques are required to separate this foreground from the cosmic signal. Free emission, also known as Bremsstrahlung, occurs when electrons scatter off ions in the interstellar medium. This process emits radiation across a wide range of frequencies, adding to the foreground contamination. Effective removal of free emission is essential for clear CMB observations. The process of separating these galactic emissions from the CMB involves multi-frequency observations. By observing the sky at various wavelengths, scientists can distinguish between the different sources of radiation. Each type of emission has a unique spectral signature, aiding in their identification and removal. Component separation algorithms are employed to handle this task. These algorithms analyze data from multiple frequencies to isolate the CMB from galactic emissions. Techniques like the internal linear combination, ILC, and maximum entropy method, MEM, are commonly used to achieve this separation. Despite these advanced methods, residual contamination can still affect the data. Even small amounts of leftover galactic emission can impact the analysis, potentially contributing to observed anomalies such as the axis of evil. Continuous refinement of these techniques is necessary to improve the accuracy of CMB measurements. The Planck satellite provided a significant improvement in our ability to manage galactic emissions. With its broad frequency coverage and high sensitivity, Planck has produced detailed maps of both the CMB and foreground emissions. This has enhanced our understanding and removal of these contaminants. Comparing data from different missions helps validate the effectiveness of galactic emission removal. Consistency across multiple datasets increases confidence that the observed features are real and not artifacts of residual foreground contamination. Galactic emission interference varies across different regions of the sky. The galactic plane in particular has high levels of emission, making it challenging to extract a clean CMB signal. Researchers often mask or exclude these regions to reduce contamination in their analysis. Cross-correlation with other datasets can help identify and mitigate the effects of galactic emissions. By comparing CMB data with independent observations, such as galactic surveys, scientists can better understand and correct for the influence of foreground contaminants. Statistical methods play a crucial role in assessing the impact of galactic emissions. By simulating the expected foreground contributions and their effects on the CMB, researchers can estimate the likelihood that observed anomalies are due to these contaminants. Continued advancements in technology and methodology are needed to address the challenges posed by galactic emissions. Future missions with improved instruments and broader frequency coverage will provide better data, helping to further isolate the CMB from foreground interference. Understanding and mitigating galactic emission interference is essential for all CMB studies. Accurate separation of these emissions is crucial not only for studying anomalies like the axis of evil, but also for testing cosmological models and refining our knowledge of the universe's origins. Ultimately, the issue of galactic emission interference highlights the complexities involved in observing the CMB. It underscores the need for ongoing innovation in observational techniques and data processing to ensure that our measurements accurately reflect the true nature of the cosmos. The axis of evil is not the only anomaly observed in the cosmic microwave background. There are several other notable anomalies that have puzzled scientists. Comparing the axis of evil with these anomalies can provide context and potentially reveal common underlying causes. One such anomaly is the cold spot. Discovered in the southern hemisphere of the CMB, the cold spot is an unusually large and cold region. Like the axis of evil, its origin is still debated, with some theories suggesting it could be a sign of a supervoid or even a collision with another universe. Another anomaly is the hemispherical asymmetry. This refers to a difference in the average temperature fluctuations between the northern and southern hemispheres of the CMB. This asymmetry challenges the assumption that the universe is isotropic on large scales, similar to the implications of the axis of evil. There is also the low quadrupole anomaly. Observations have shown that the power of the quadrupole moment is lower than predicted by the standard cosmological model. This deviation raises questions about the initial conditions of the universe and the accuracy of inflationary models. The alignment of the quadrupole and octupole moments, which contributes to the axis of evil, also appears in other multipoles, suggesting a more pervasive alignment issue. These alignments are unexpected and not easily explained by current cosmological theories. Comparing these anomalies reveals that they often challenge the same fundamental assumptions, such as the isotropy and homogeneity of the universe. This consistency across different anomalies might indicate a need for new physics or a deeper understanding of the early universe. The anomalies also share common features in their statistical properties. For example, both the axis of evil and the hemispherical asymmetry show significant deviations from the expected random distribution of temperature fluctuations. This suggests that the anomalies are not just random fluctuations but could have a common cause. Some researchers propose that these anomalies might be linked through large-scale cosmic structures. If the universe has regions with different properties or histories, these structures could influence multiple aspects of the CMB, creating a range of observed anomalies. Foreground contamination and instrumental errors are also potential common causes. If these factors are not fully accounted for, they could introduce similar artifacts into the CMB data. Rigorous testing and cross-validation are necessary to rule out these possibilities. Exploring the connections between different anomalies can lead to new theoretical models. These models might incorporate additional fields, complex topologies, or novel physical processes that can explain multiple anomalies simultaneously. Future missions with higher sensitivity and resolution will be crucial for studying these anomalies in greater detail. Improved data will help determine whether the anomalies are truly connected and what underlying mechanisms might be responsible. The comparison also highlights the importance of statistical rigor, ensuring that the observed anomalies are not just results of data analysis methods or selection effects is critical. This requires careful design of experiments and thorough testing of statistical models. Understanding these anomalies could provide new insights into fundamental physics. They might reveal previously unknown aspects of cosmic inflation, dark matter, or dark energy. This could lead to significant advancements in our understanding of the universe's formation and evolution. Ultimately, the comparison with other anomalies underscores the complexity of the CMB and the universe it reveals. It highlights the need for continued exploration, innovation, and collaboration in cosmology. Each anomaly provides a piece of the puzzle, contributing to a deeper understanding of the cosmos. The large-scale structure of the universe refers to the distribution and organization of galaxies, clusters and superclusters across vast cosmic distances. This structure forms a complex web of matter, often described as the cosmic web, which includes filaments, voids, and walls of galaxies. Understanding the large-scale structure is crucial because it provides insights into the fundamental processes that shape the universe. These structures formed from the initial density fluctuations in the early universe, which grew over time due to gravitational attraction. The study of large-scale structure helps us test and refine cosmological models. By comparing observations with theoretical predictions, scientists can validate or challenge our understanding of the universe's evolution, including the effects of dark matter and dark energy. Galaxies are not randomly scattered but are found in groups and clusters, connected by filaments of dark matter. These patterns are the result of gravitational forces acting over billions of years, pulling matter into denser regions and creating vast empty spaces known as voids. Observing the large-scale structure allows scientists to measure key cosmological parameters, such as the total amount of matter and energy in the universe. These measurements are essential for understanding the dynamics and fate of the cosmos. One important feature of the large-scale structure is the Barion acoustic oscillations, BAOs. These are regular periodic fluctuations in the density of visible matter, resulting from sound waves that propagated through the early universe. BAOs serve as a standard ruler for measuring cosmic distances and the expansion rate of the universe. The large-scale structure also provides clues about the nature of dark matter. While dark matter does not emit light, its presence is inferred from its gravitational effects on visible matter. By studying the distribution of galaxies and clusters, scientists can map the underlying dark matter. Gravitational lensing, the bending of light by massive objects, is another tool for studying the large-scale structure. This phenomenon allows astronomers to probe the distribution of dark matter and the geometry of the universe by observing how light from distant galaxies is distorted. The large-scale structure is also influenced by dark energy, which is driving the accelerated expansion of the universe. By analyzing the distribution and growth of cosmic structures, scientists can learn more about the properties of dark energy and its impact on the universe's evolution. Redshift surveys, which measure the distance and velocity of galaxies, are essential for mapping the large-scale structure. These surveys provide a three-dimensional view of the universe, revealing the intricate web of galaxies and clusters that make up the cosmic landscape. Understanding the large-scale structure has practical implications for other areas of astrophysics. For instance, it helps us understand the environments in which galaxies form and evolve, shedding light on the processes that lead to the formation of stars and planets. The study of the large-scale structure also addresses fundamental questions about the universe's initial conditions. By tracing the development of cosmic structures from the Big Bang to the present day, scientists can gain insights into the early universe and the forces that shaped it. Large-scale structure research often involves large collaborations and advanced technologies. Projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, collect vast amounts of data, requiring sophisticated analysis techniques and powerful computing resources. Future missions, such as the Euclid Satellite and the Large Synoptic Survey Telescope, LSST, will provide even more detailed observations of the large-scale structure. These missions aim to map billions of galaxies, offering unprecedented insights into the universe's composition and evolution. In summary, the large-scale structure of the universe is a fundamental aspect of cosmology. Its study helps us understand the distribution of matter, the nature of dark matter and dark energy, and the overall dynamics of the cosmos. By exploring this structure, we gain crucial insights into the history and fate of the universe. The alignment with the axis of evil suggests a potential connection between the large-scale structure of the universe and the anomalies observed in the cosmic microwave background. This alignment indicates that there might be a directional dependence in the distribution of cosmic structures. If the large-scale structure is aligned with the axis of evil, it could imply that the initial conditions of the universe were not isotropic. Instead, there may have been preferred directions that influence the formation and distribution of galaxies and clusters. One possibility is that large-scale cosmic structures, such as superclusters or vast filaments of galaxies, have a directional alignment that matches the axis of evil. This could be a relic of the early universe's dynamics, where certain directions experience different rates of expansion or matter distribution. The alignment could also suggest that there are underlying physical mechanisms that connect the large-scale structure to the CMB anomalies. These mechanisms might involve interactions between dark matter, dark energy, and ordinary matter that create large-scale anisotropies. This connection might help explain why the axis of evil persists across different data sets and observational missions. If it is tied to the large-scale structure, it would be a consistent feature rather than a random fluctuation or an artifact of data processing. The study of this alignment involves comparing maps of the CMB with maps of the large-scale structure. Researchers analyze the positions and orientations of galaxies, clusters, and superclusters to see if they correlate with the patterns observed in the CMB. Cross-correlating these maps can reveal whether there is a statistically significant alignment. If a strong correlation is found, it would support the hypothesis that the axis of evil is linked to the large-scale distribution of matter in the universe. This alignment could also impact our understanding of cosmic inflation. If the initial conditions of inflation had directional dependencies, It would challenge the standard model of a perfectly isotropic inflationary period. New models might be needed to account for these anisotropies. Additionally, the alignment might provide insights into the nature of dark matter and dark energy. If these components influence the large-scale structure in anisotropic ways, it could explain both the distribution of galaxies and the patterns observed in the CMB. Understanding this alignment is crucial for refining our cosmological models. It could lead to new theories about the universe's initial conditions, the behavior of dark matter and dark energy, and the overall dynamics of cosmic evolution. Future observations will be key to studying this alignment in greater detail. Missions that map the large-scale structure, with higher precision and broader coverage, will help determine whether the axis of evil is truly connected to the distribution of cosmic structures. Advanced simulations of cosmic structure formation can also shed light on this alignment. By modeling different initial conditions and physical processes, researchers can explore how anisotropies might develop and whether they match the observed patterns. The potential connection between the axis of evil and the large-scale structure highlights the complexity of the universe. It suggests that there are still fundamental aspects of cosmic evolution that we do not fully understand, requiring continued exploration and innovation. Ultimately, the alignment with the axis of evil represents an intriguing puzzle in cosmology. Solving this puzzle could provide profound insights into the nature of the universe and its underlying principles, advancing our knowledge of the cosmos. The potential connections between the axis of evil and the large-scale structure of the universe have inspired various theories. One such theory suggests that the alignment could be a remnant of the initial conditions of the universe, indicating a non-isotropic state during the Big Bang. Another theory posits that cosmic inflation, the rapid expansion of the universe immediately after the Big Bang, may not have been perfectly uniform. This imperfect inflation could have seeded the universe with directional dependencies, leading to the observed alignments. Some researchers propose that the alignment could be due to topological defects in the fabric of spacetime. These defects, such as cosmic strings or domain walls, could create large-scale anisotropies in the CMB and the distribution of matter. There is also the hypothesis that large-scale magnetic fields could influence the alignment. If these fields were present during the early universe, they could leave imprints on both the CMB and the large-scale structure, creating the observed directional patterns. Dark matter interactions provide another potential connection. If dark matter has properties that vary directionally, it could affect the formation of cosmic structures and the CMB's temperature fluctuations, contributing to the axis of evil. The influence of dark energy is another avenue of exploration. If dark energy's effects are not uniform but have a directional component, this could lead to anisotropies in the expansion rate of the universe and the distribution of cosmic structures. Gravitational waves from the early universe could also play a role. These ripples in spacetime, if they were anisotropic, could impact the large-scale structure and the CMB, creating alignments similar to the axis of evil. Another theory involves the interaction between our universe and other possible universes in a multiverse scenario. Collisions or gravitational interactions with other universes could leave directional imprints on our own universe, explaining the alignment. Quantum fluctuations during the inflationary period might also provide a connection. If these fluctuations had directional biases, they could influence the large-scale structure and the CMB, resulting in the observed patterns. The role of anisotropic expansion phases is another area of interest. If the universe underwent different expansion rates in various directions at certain stages, this could create lasting alignments in the large-scale structure and the CMB. Studies of the cosmic web, the large-scale structure of the universe, might reveal more about these connections. If the filaments and voids of the cosmic web show alignments that match the axis of evil, it would support the idea of a directional influence on cosmic evolution. Another intriguing theory is that of a varying fine structure constant. If this fundamental constant of nature changes over time or space, it could create anisotropies in both the CMB and the large-scale structure, providing a potential explanation for the alignment. There is also the possibility that the alignment is a signal of new physics beyond the standard model. Unexplored forces or particles might influence the universe's large-scale structure and the CMB, leading to the observed patterns. Some researchers suggest that the alignment could be due to a bias in our observational techniques or the data processing methods. Thorough investigation and cross-validation with different methods and data sets are necessary to rule out this possibility. Ultimately, exploring these potential connections and theories is crucial for understanding the axis of evil. Continued research, new observations, and advanced simulations will help clarify whether these alignments are a window into new physics or a deeper understanding of the universe's initial conditions and evolution. Observational evidence is key to understanding the axis of evil and its implications. The cosmic microwave background, or CMB, has been extensively studied by several missions, providing detailed maps of the early universe. The Wilkinson Microwave Anisotropy Probe, or WMAP, was one of the first missions to detect the axis of evil. WMAP's observations revealed unexpected alignments in the quadrupole and octupole moments of the CMB, which sparked significant interest and debate. Following WMAP, the Planck satellite offered even higher resolution maps of the CMB. Planck's data confirmed the presence of the axis of evil, showing similar alignments and providing more detailed information about the temperature fluctuations in the CMB. Planck's observations also included measurements of the CMB's polarization. These polarization data provide additional evidence for the axis of evil, as they show similar alignments in the polarization patterns, reinforcing the anomaly's significance. Cross-correlation studies have been conducted to compare the CMB data with other cosmic signals. These studies help to determine whether the alignments are unique to the CMB, or if they appear in other datasets, providing a broader context for the anomaly. Ground-based observatories like the Atacama Cosmology Telescope and the South Pole Telescope have also contributed to the study of the CMB. These observatories provide complementary data, which help to verify the findings from space-based missions. The consistency of the axis of evil across different missions and observatories strengthens the case that it is a real feature of the universe, rather than an artifact of any single data set or instrument. This robustness is crucial for its acceptance in the scientific community. Foreground removal techniques are essential for isolating the true CMB signal from galactic emissions and other sources of contamination. Advanced algorithms have been developed to ensure that the observed alignments are not due to residual foreground interference. Statistical analyses play a vital role in evaluating the significance of the axis of evil. By comparing the observed alignments with simulations of random CMB maps, researchers can assess the likelihood that these patterns are genuine rather than coincidental. The alignment has also been studied in the context of large-scale structure surveys. These surveys map the distribution of galaxies and galaxy clusters, providing a three-dimensional view of the universe that can be compared with the CMB data. Redshift surveys, which measure the distance and velocity of galaxies, help to understand the large-scale structure and its potential connection to the axis of evil. These surveys provide additional observational evidence that can support or challenge the anomaly. Gravitational lensing studies, which observe the bending of light by massive objects, offer another way to probe the large-scale structure of the universe. Lensing data can be compared with CMB observations to see if there are any correlations with the axis of evil. Future missions and observatories, such as the Simons Observatory and the Large Synoptic Survey Telescope, will provide even more detailed observations of the CMB and the large-scale structure. These new data will be critical for further investigating the axis of evil. Continued analysis of existing data is also important. As new techniques and methods are developed, reanalyzing the CMB data can provide fresh insights and help to refine our understanding of the observed alignments. Ultimately, observational evidence is the foundation for studying the axis of evil. It guides theoretical work, informs our understanding of the universe, and helps to determine whether this anomaly is a profound discovery or a statistical curiosity. Theoretical models and simulations are crucial for understanding the axis of evil. They help researchers explore various scenarios and predict how different conditions could lead to the observed alignments in the CMB. Cosmic inflation is a key component of these models. Inflationary theory suggests that the universe underwent a rapid expansion shortly after the Big Bang, smoothing out any initial irregularities. Modifying this theory to include anisotropies could potentially explain the axis of evil. One approach involves introducing new fields or particles that could influence inflation. These additional components might create directional dependencies in the inflationary process. leading to the large-scale alignment seen in the CMB. Another avenue of research explores topological defects in the early universe. Defects like cosmic strings or domain walls could disrupt the uniformity of the CMB, creating patterns that match the axis of evil. Simulations of these scenarios help test their viability. Large-scale simulations of cosmic structure formation are essential for studying these theories. These simulations model the evolution of the universe from its earliest moments to the present day, incorporating various physical processes and initial conditions. By comparing these simulations with actual observations, researchers can test different hypotheses about the origin of the axis of evil. If a simulation reproduces the observed alignments, it provides strong evidence for the underlying theory. Simulations also allow scientists to explore the impact of dark matter and dark energy on the large-scale structure of the universe. If these components have anisotropic properties, they could influence the CMB in ways that create the axis of evil. The role of large-scale magnetic fields is another area of interest. If such fields were present during the early universe, they could leave imprints on both the CMB and the distribution of matter. Simulations can help determine if magnetic fields could produce the observed alignments. Gravitational waves from the early universe are another potential factor. If these waves had directional properties, they could impact the large-scale structure and the CMB. Simulating the effects of gravitational waves helps test this hypothesis. The interaction between our universe and other possible universes is an intriguing idea. In a multiverse scenario, collisions or gravitational interactions with other universes could leave directional imprints. Simulations of these interactions can explore this possibility. Quantum fluctuations during inflation might also play a role. If these fluctuations had directional biases, they could influence the CMB and the large-scale structure. Modeling these fluctuations provides insights into their potential impact. The varying fine-structure constant hypothesis suggests that this fundamental constant of nature changes over time or space. If true, it could create anisotropies in both the CMB and the large-scale structure. Simulations of varying constants help test this idea. Advanced computational techniques are essential for these simulations. High-performance computing resources allow researchers to model the complex processes of cosmic evolution with greater precision and detail than ever before. Comparing different theoretical models and their predictions is a key part of this research. By analyzing the results of various simulations, scientists can identify which models best match the observed data and refine their theories accordingly. Continued advancements in simulations and theoretical models will be crucial for understanding the axis of evil. As new data becomes available from future observations, these models will be updated and tested, helping to unravel the mysteries of this intriguing anomaly. The measurement of the Hubble constant is a fundamental task in cosmology. The Hubble constant describes the rate at which the universe is expanding. It's usually expressed in kilometers per second per megaparsec, indicating how fast galaxies are receding from each other as a function of their distance. Accurately determining the Hubble constant is crucial for understanding the age, size, and fate of the universe. There are two primary methods used to measure this constant: the traditional distance ladder method and observations of the cosmic microwave background. The distance ladder method relies on a series of steps to measure distances to astronomical objects. It begins with the most nearby objects, such as Cepheid variable stars, whose intrinsic brightness is well known. By comparing their known brightness to their observed brightness, astronomers can calculate their distance. These distance measurements are then used to calibrate other distance indicators, such as type Ia supernovae. These supernovae have a consistent peak brightness, making them excellent standard candles for measuring distances to faraway galaxies. Edwin Hubble first measured the expansion rate of the universe using observations of galaxies. He found that galaxies are moving away from us, and their speed is proportional to their distance. This relationship is described by the Hubble constant. Observations of the cosmic microwave background provide another method for measuring the Hubble constant. By analyzing the detailed temperature fluctuations in the CMB, scientists can infer the rate of expansion in the early universe. Data from missions like the Planck satellite have provided precise measurements of the CMB, leading to an estimated value of the Hubble constant. However, this value differs slightly from those obtained using the distance ladder method. This discrepancy between different methods of measuring the Hubble constant is known as the Hubble tension. It's one of the major unsolved problems in cosmology, suggesting that there might be unknown factors or new physics at play. One possible explanation for the Hubble tension could involve new types of dark energy or modifications to the standard model of cosmology. Researchers are actively exploring these possibilities to understand why different methods yield different values. Improving the precision of Hubble constant measurements is a key goal for current and future observations. Advanced telescopes and better calibration of distance indicators are crucial for refining these measurements and resolving the Hubble tension. Gravitational lensing offers another way to measure the Hubble constant. By observing how light from distant objects is bent by massive foreground galaxies, astronomers can infer the expansion rate of the universe. The use of gravitational wave observations is a relatively new method. When neutron stars or black holes merge, they emit gravitational waves. The distance to these events can be measured directly, providing an independent way to estimate the Hubble constant. Further research into the local environment and potential systematic errors in measurements is also important. Understanding and correcting for any biases in the data can help achieve more accurate determinations of the Hubble constant. The James Webb Space Telescope is expected to provide new insights into the Hubble constant. Its advanced capabilities will allow for more precise measurements of distant astronomical objects, contributing to our understanding of cosmic expansion. Ultimately, the measurement of the Hubble constant is a central issue in cosmology. Resolving the discrepancies between different methods will help clarify our understanding of the universe's expansion and may reveal new physics that could revolutionize our knowledge of the cosmos. The curvature of the universe is a fundamental aspect of cosmology, determining the overall shape and fate of the cosmos. It describes whether the universe is flat, open, or closed. Understanding the curvature helps us comprehend the universe's geometry and its ultimate destiny. If the universe is flat, it means that parallel lines will remain parallel forever, and the geometry of space follows Euclidean principles. This scenario suggests that the universe will continue to expand indefinitely, but at a decelerating rate if only considering matter and dark matter. An open universe has a negative curvature similar to a saddle shape. In this model, parallel lines eventually diverge, and the universe expands forever, accelerating over time. This geometry implies an infinite, unbounded universe that grows without end. A closed universe has a positive curvature, like the surface of a sphere. In this model, parallel lines eventually converge, and the universe might eventually stop expanding and begin to contract, leading to a possible big crunch. The cosmic microwave background plays a crucial role in determining the curvature of the universe. By analyzing the temperature fluctuations in the CMB, scientists can infer the geometry of space. The pattern of these fluctuations provides insights into the overall shape of the universe. Data from the Planck satellite has shown that the universe is remarkably flat, with a slight margin of error. This flatness suggests that the universe's total energy density is very close to the critical density required to make the universe geometrically flat. The measurement of the Hubble constant also affects our understanding of the universe's curvature. Different values for the Hubble constant can imply different rates of expansion, which in turn influence our calculations of the universe's geometry. The Hubble tension, the discrepancy between different methods of measuring the Hubble constant, complicates our understanding of curvature. Resolving this tension is essential for accurately determining the universe's shape and its expansion history. Dark energy has a significant impact on the curvature of the universe. As the dominant force driving the accelerated expansion, dark energy's properties and distribution affect the overall geometry. Understanding dark energy is crucial for comprehending the universe's curvature. Gravitational lensing provides another method to study the curvature. By observing how light is bent by massive objects, astronomers can infer the geometry of space. These observations help confirm whether the universe is flat, open, or closed. Large-scale structure surveys, which map the distribution of galaxies and galaxy clusters, also contribute to our understanding of curvature. These surveys provide a three-dimensional view of the universe, helping to reveal its overall shape and structure. Theoretical models of cosmic inflation suggest that the universe should be very close to flat. Inflationary theory predicts that any initial curvature would have been stretched out, making the observable universe appear flat. This prediction aligns well with current observations. Future missions and observatories will provide more precise measurements of the CMB and large-scale structure, helping to refine our understanding of the universe's curvature. Improved data will allow for more accurate calculations and potentially resolve existing discrepancies. Understanding the curvature of the universe also has implications for its fate. A flat universe suggests endless expansion, while a closed universe might eventually collapse. Determining the curvature helps predict the long-term behavior of the cosmos. Ultimately, the study of the universe's curvature is a fundamental aspect of cosmology. It connects our understanding of the universe's geometry, expansion, and fate. By continuing to refine our measurements and theories, we move closer to a comprehensive understanding of the cosmos and its underlying principles. The cosmic density parameter, often denoted as omega O, is a crucial factor in cosmology. It represents the ratio of the actual density of the universe to the critical density needed for the universe to be flat. Understanding this parameter helps determine the overall fate and structure of the universe. If omega is equal to 1, the universe is exactly at the critical density and is flat. This flatness implies that the universe will expand forever, but at a rate that slows down over time. Current measurements from the cosmic microwave background suggest that omega is very close to 1. When omega is greater than 1, the universe has a density higher than the critical density, indicating a closed universe. This means that the universe could eventually stop expanding and start contracting, potentially leading to a big crunch. If omega is less than 1, the universe has a density lower than the critical density, suggesting an open universe. In this scenario, the universe will expand forever, and its expansion will accelerate over time due to dark energy. Dark matter and dark energy are significant contributors to the cosmic density parameter. Dark matter contributes to the gravitational pull that affects the expansion rate, while dark energy drives the accelerated expansion of the universe. Understanding these components is essential for accurate measurements of omega. The cosmic microwave background provides critical data for calculating omega. By analyzing the temperature fluctuations in the CMB, scientists can infer the overall density of the universe. This information helps to determine whether the universe is open, closed, or flat. Gravitational lensing, which involves observing how light from distant objects is bent by massive foreground objects, offers another method to measure the cosmic density parameter. This technique helps map the distribution of dark matter and contributes to our understanding of the universe's total density. Large-scale structure surveys, which map the distribution of galaxies and galaxy clusters, also play a crucial role. These surveys provide a three-dimensional view of the universe's matter distribution, allowing scientists to estimate the total mass and, consequently, the cosmic density parameter. The Hubble constant, which measures the rate of the universe's expansion, is directly related to omega. Accurate measurements of the Hubble constant help refine our understanding of the cosmic density parameter and its implications for the universe's geometry and fate. The Hubble tension, or the discrepancy between different methods of measuring the Hubble constant, complicates our understanding of omega. Resolving this tension is vital for accurate determinations of the cosmic density parameter and for clarifying the nature of dark energy and dark matter. Dark energy's influence on the cosmic density parameter is profound. As the dominant component of the universe's energy budget, dark energy affects the overall dynamics and expansion rate. Understanding its properties is crucial for accurately determining omega. Theoretical models of cosmic inflation predict that the universe should be very close to flat, implying that omega should be near 1. This prediction aligns well with current observations, suggesting that the universe is at or very close to the critical density. Future missions and observatories, such as the James Webb Space Telescope and the Euclid satellite, will provide more precise measurements of the cosmic density parameter. These new data will help refine our understanding of omega and address existing discrepancies. Understanding the cosmic density parameter has implications for the universe's fate. A flat universe, where omega equals 1, will continue to expand indefinitely. A closed universe could eventually collapse, while an open universe will expand forever at an accelerating rate. In summary, the cosmic density parameter is a fundamental aspect of cosmology that influences our understanding of the universe's structure, dynamics, and ultimate fate. By continuing to refine our measurements and models, we enhance our comprehension of the cosmos and its fundamental properties. Barion acoustic oscillations, or BAOs, are periodic fluctuations in the density of visible matter in the universe. They originated from sound waves that propagated through the early universe's hot plasma. These sound waves left imprints on the large-scale structure we observe today. The study of BAOs is crucial for understanding the universe's expansion history. They serve as a standard ruler for measuring cosmic distances. By comparing the observed scale of BAOs with theoretical predictions, scientists can determine the rate of expansion at different epochs. Changes in the scale of BAOs provide insights into the dynamics of the universe. If the scale changes, it indicates variations in the expansion rate, which can be linked to the properties of dark energy and the overall matter content of the universe. Observations from galaxy surveys, such as the Sloan Digital Sky Survey, have mapped BAOs across vast cosmic distances. These surveys measure the distribution of galaxies and detect the characteristic scale of BAOs, providing a three-dimensional view of the universe. The cosmic microwave background also provides information about BAOs. The early universe's sound waves left imprints on the CMB, which we observe as temperature fluctuations. These imprints help calibrate the BO scale and refine our measurements. Future missions, like the Dark Energy Spectroscopic Instrument, aim to map millions of galaxies and further improve our understanding of BAOs. These missions will provide more precise measurements of the BAO scale and enhance our knowledge of cosmic expansion. Changes in BAOs can reveal the influence of dark energy. If dark energy's properties vary over time or space, it could affect the expansion rate and alter the BAO scale. Studying these changes helps constrain models of dark energy and its role in the universe. The relationship between BAOs and the Hubble constant is also significant. Accurate measurements of the BAO scale help determine the Hubble constant, which describes the universe's current expansion rate. This relationship is crucial for resolving the Hubble tension. Theoretical models of cosmic inflation predict specific features in the BAO scale. These features provide a test for inflationary theories, helping to confirm or challenge our understanding of the early universe. Changes in BAOs can indicate deviations from these predictions. Gravitational lensing studies can complement BAO measurements. By observing how light from distant galaxies is bent by massive objects, scientists can map the distribution of dark matter and refine their understanding of the BAO scale. Changes in the BAO scale over time can provide a detailed history of the universe's expansion. By measuring BAOs at different redshifts, researchers can trace how the expansion rate has evolved and gain insights into the effects of dark energy and dark matter. The precision of BAO measurements is continually improving. Advanced instruments and techniques allow for more accurate detection and analysis of BAOs, leading to better constraints on cosmological models and parameters. BAOs also play a role in understanding the large-scale structure of the universe. They influence the distribution of galaxies and clusters, contributing to the overall pattern we observe. Changes in BAOs can reveal new information about the formation and evolution of cosmic structures. Cross-correlating BAO measurements with other cosmic observations, such as supernovae and the cosmic microwave background, provides a comprehensive picture of the universe's expansion. This multifaceted approach enhances the reliability and accuracy of our cosmological models. Ultimately, the study of Barion acoustic oscillations is essential for understanding the universe's expansion history and the properties of dark energy. By continuing to improve our measurements and theoretical models, we gain deeper insights into the fundamental nature of the cosmos. The cosmic power spectrum is a crucial tool for understanding the distribution of matter in the universe. It describes how density fluctuations vary with scale, providing insights into the underlying physics that shape the cosmos. The power spectrum is derived from observations of the cosmic microwave background and the large-scale structure of the universe. It helps to quantify the strength of fluctuations at different scales, revealing the processes that influence their growth. Barion acoustic oscillations, or BAOs, leave a distinct imprint on the power spectrum. These regular periodic fluctuations create peaks in the power spectrum, corresponding to the scale of the sound waves in the early universe. These peaks are essential for calibrating cosmological models. The amplitude and position of the peaks in the power spectrum are sensitive to various cosmological parameters. For instance, the matter density, dark energy properties, and the Hubble constant all influence the shape and features of the power spectrum. Changes in the power spectrum provide insights into the nature of dark matter and dark energy. If these components have properties that vary over time or space, they will affect the growth of structures and leave detectable signatures in the power spectrum. The power spectrum also helps to test theories of cosmic inflation. Inflationary models predict a specific distribution of fluctuations, which can be compared to the observed power spectrum. Any deviations from these predictions can indicate new physics or the need to refine existing models. Gravitational lensing affects the power spectrum by distorting the observed distribution of matter. This phenomenon must be accounted for when interpreting the power spectrum, as it can introduce biases that affect our understanding of cosmological parameters. Redshift space distortions, caused by the peculiar velocities of galaxies, also influence the power spectrum. These distortions provide additional information about the growth of structure and the distribution of matter, enhancing the utility of the power spectrum for cosmological studies. The cosmic power spectrum is closely linked to the cosmic density parameter, omega. By analyzing the power spectrum, scientists can determine the total density of the universe and its components, such as dark matter and dark energy. This information is crucial for understanding the universe's geometry and fate. High-precision measurements of the power spectrum come from missions like the Planck satellite, which provided detailed maps of the CMB. These observations are complemented by large-scale structure surveys, such as the Sloan Digital Sky Survey, which map the distribution of galaxies. Future missions will continue to refine our understanding of the power spectrum. Projects like the Dark Energy Spectroscopic Instrument and the Euclid satellite aim to provide even more precise measurements, enhancing our ability to probe the fundamental nature of the universe. Cross-correlation with other datasets, such as gravitational lensing maps and supernova surveys, helps to validate the power spectrum measurements. This multifaceted approach ensures the robustness of the conclusions drawn from the power spectrum. The power spectrum also reveals information about the initial conditions of the universe. By studying the distribution of fluctuations, scientists can infer the properties of the primordial universe and the processes that led to the formation of galaxies and clusters. Understanding the cosmic power spectrum is essential for testing the standard model of cosmology. Any discrepancies between the observed power spectrum and theoretical predictions could indicate new physics, such as modifications to general relativity or the presence of exotic particles. Ultimately, the cosmic power spectrum is a fundamental aspect of cosmology. It provides a comprehensive picture of the universe's structure, revealing the underlying processes that shaped the cosmos. By continuing to refine our measurements and models, we deepen our understanding of the universe and its origins. The axis of evil refers to unexpected alignments in the cosmic microwave background, challenging the assumption that the universe is isotropic. This anomaly was first observed by the Wilkinson microwave anisotropy probe and confirmed by the Planck satellite. The cosmic microwave background is the afterglow of the Big Bang, providing a snapshot of the early universe. It's a crucial tool for understanding the universe's origins, structure, and evolution. The alignment of the quadrupolar and octopolar moments in the CMB suggests a preferred direction, contradicting the cosmological principle that the universe is the same in all directions on large scales. Various hypotheses have been proposed to explain the axis of evil, including foreground contamination, instrumental errors, and statistical flukes. Each hypothesis has been rigorously tested, yet the anomaly persists. The foreground contamination hypothesis suggests that emissions from our galaxy could create the observed alignments. Sophisticated algorithms are used to separate these foregrounds from the true CMB signal. Instrumental errors could also account for the anomaly. Imperfections in the detectors or data processing methods might introduce artifacts. However, the consistency across different missions suggests this is unlikely. Statistical fluke arguments propose that the alignment could be a random occurrence. Extensive simulations and statistical analyses have been conducted to assess this possibility, but the anomaly remains significant. The axis of evil has implications for the standard cosmological model, including cosmic inflation. If inflation wasn't perfectly uniform, it could lead to the large-scale alignment seen in the CMB. Large-scale structures in the universe, such as superclusters and filaments, might be aligned with the axis of evil. This suggests a connection between these structures and the early universe's dynamics. The cosmic power spectrum is influenced by Barion acoustic oscillations, which leave distinct imprints. These imprints help measure the expansion rate and test cosmological models. Changes in the Barion acoustic oscillations provide insights into the universe's expansion history and the properties of dark energy and dark matter. Accurate measurements of these changes are crucial for refining our models. The cosmic density parameter, omega, determines whether the universe is flat, open, or closed. Observations suggest the universe is very close to flat, implying omega is near 1. Understanding the Hubble constant, which describes the universe's expansion rate, is essential. Different methods yield slightly different values, leading to the Hubble tension, a major issue in cosmology. The curvature of the universe influences its fate. A flat universe suggests endless expansion, while a closed universe might eventually collapse. Current data points to a flat universe, but the exact curvature is still being refined. Overall, the study of the axis of evil and its implications is a dynamic field. Ongoing research and future observations aim to resolve the mysteries it presents, deepening our understanding of the universe. Research on the axis of evil is ongoing, with scientists continually exploring its implications and potential explanations. Advanced observational techniques and new missions aim to provide more detailed data to refine our understanding of this anomaly. The Planck satellite has provided the most precise measurements of the CMB to date. Its data continue to be analyzed, revealing more about the large-scale structure of the universe and the anomalies within it, including the axis of evil. Ground-based observatories like the Atacama Cosmology Telescope and the South Pole Telescope complement space missions. They provide additional data that help verify and refine the findings from satellites, contributing to a comprehensive understanding of the CMB. The Dark Energy Survey and the Sloan Digital Sky Survey are crucial for mapping the large-scale structure of the universe. These surveys provide three-dimensional maps of galaxy distributions, helping to explore potential connections with the axis of evil. Future missions, such as the Simons Observatory and the Euclid satellite, are expected to provide even more precise measurements of the CMB and large-scale structure. These missions will help address current uncertainties and further investigate the axis of evil. The Hubble tension remains a significant issue in cosmology. Resolving the discrepancy between different measurements of the Hubble constant is crucial for understanding the universe's expansion rate and refining cosmological models. Advanced statistical techniques are being developed to better analyze CMB data. These methods aim to reduce uncertainties and improve the accuracy of measurements, helping to determine whether the axis of evil is a real feature or a statistical fluke. The role of foreground contamination continues to be a major focus. Researchers are developing new algorithms and methods to better separate the CMB signal from galactic emissions and other sources of interference. Theoretical models are being expanded to include potential new physics that could explain the axis of evil. These models explore possibilities such as anisotropic inflation, large-scale magnetic fields, and interactions with other universes. Simulations of cosmic structure formation are becoming increasingly sophisticated. These simulations help test different hypotheses about the origin of the axis of evil and its connection to the large-scale structure of the universe. Cross-correlation studies are being conducted to compare CMB data with other cosmic signals. These studies help determine whether the observed alignments are unique to the CMB or if they appear in other datasets, providing a broader context for the anomaly. Research on the cosmic power spectrum is advancing, with more precise measurements of Barion acoustic oscillations. These measurements are crucial for understanding the universe's expansion history and the properties of dark energy and dark matter. The cosmic density parameter, omega, continues to be refined. Accurate measurements of omega are essential for understanding the geometry of the universe and its ultimate fate. Gravitational lensing studies are providing new insights into the distribution of dark matter. These observations help map the large-scale structure and refine our understanding of the cosmic power spectrum and the axis of evil. Overall, the current state of research on the axis of evil is dynamic and evolving. With ongoing observations, advanced simulations, and new theoretical models, scientists are gradually piecing together the puzzle of this intriguing anomaly. The quest to understand the axis of evil continues to drive progress in cosmology, pushing the boundaries of our knowledge about the universe. Many questions remain about the axis of evil. One of the primary mysteries is whether the alignment observed in the CMB is a genuine feature of the universe or a result of some unknown bias in our measurements or data processing methods. If the axis of evil is real, what could have caused such a large-scale anisotropy in the universe? This question drives much of the current theoretical work, seeking to understand the early universe's conditions that could have led to this unexpected alignment. The role of cosmic inflation in the axis of evil is another major question. If inflation was not perfectly isotropic, what mechanism could have introduced a preferred direction, and how does this fit with our current understanding of inflationary models? How do dark matter and dark energy contribute to the observed anomalies? Understanding their properties and interactions is crucial, as they make up the majority of the universe's content and significantly influence its large-scale structure. What other unknown factors might be influencing the CMB? Are there physical processes or cosmic structures we have yet to discover that could explain the axis of evil and other anomalies in the CMB? The Hubble tension raises questions about our measurement techniques and the underlying physics. Why do different methods yield different values for the Hubble constant? And what does this discrepancy tell us about the universe's expansion? How can we improve our methods to separate the CMB signal from foreground contamination more effectively? Better algorithms and observational techniques are needed to ensure that our data accurately reflect the true cosmic signal. What are the implications of the axis of evil for the cosmological principle? If the universe is not isotropic on large scales, how does this change our understanding of the universe's fundamental properties and the validity of our current models? Could the axis of evil be a signal of new physics beyond the standard model? Exploring this possibility might reveal unknown forces or particles that influence the universe on large scales. What role do large-scale magnetic fields play in the universe? If they exist, how might they contribute to the observed alignments in the CMB and the large-scale structure of the cosmos? Are there other anomalies in the CMB or the large-scale structure that we have not yet detected? Continued observations and more sensitive instruments might reveal additional features that challenge our current understanding. How can we reconcile the results from different cosmological surveys and missions? Ensuring that data from various sources are consistent and complementary is crucial for building a coherent picture of the universe. What can future missions and observatories teach us about the axis of evil? As technology advances, new instruments will provide more precise data, helping to resolve existing mysteries and uncover new ones. How do we address the statistical nature of cosmic anomalies? Developing robust statistical methods to distinguish genuine features from random fluctuations is essential for interpreting cosmological data accurately. Finally, what does the axis of evil tell us about the ultimate fate of the universe? Understanding the large-scale structure and dynamics of the cosmos can provide insights into how the universe will evolve over time and its eventual destiny. The search for answers to these questions continues to drive the field of cosmology forward. Continued investigation into the axis of evil is crucial for advancing our understanding of the universe. This anomaly challenges fundamental assumptions in cosmology, and studying it could lead to groundbreaking discoveries. Ongoing research helps refine our measurement techniques. As we improve our instruments and methods, we gain more accurate data, which is essential for confirming or refuting the existence of the axis of evil. Exploring the axis of evil could reveal new physics. If this anomaly is real, it might indicate forces or particles beyond the standard model, offering a deeper understanding of the universe's fundamental components. Continued investigation drives the development of better observational technology, Missions like the Simons Observatory and the Euclid satellite are designed to provide more detailed and precise data, enhancing our ability to study cosmic anomalies. Understanding the axis of evil could improve our knowledge of cosmic inflation. If the anomaly is linked to the early universe's conditions, it could provide insights into how inflation occurred and what mechanisms were involved. The research has implications for dark matter and dark energy. Studying how these components might contribute to the axis of evil helps refine our models of the universe's composition and dynamics. Ongoing studies support the refinement of cosmological models. By testing and updating these models against new data, we ensure they accurately reflect the universe's true nature and behavior. Investigating the axis of evil aids in resolving the Hubble tension. By understanding the anomaly's implications, we might uncover reasons for the discrepancy between different measurements of the Hubble constant. Continued research fosters international collaboration. Scientists from around the world contribute to the study of the axis of evil, sharing data, techniques, and insights to advance our collective understanding. Exploring this anomaly encourages the development of new theoretical frameworks. As we seek to explain the axis of evil, we may develop new theories that better describe the universe's large-scale structure and evolution. The study of the axis of evil can enhance our understanding of cosmic microwave background anomalies. By investigating this specific anomaly, we can develop methods and insights applicable to other unexplained features in the CMB. Continued investigation is essential for training the next generation of cosmologists. Working on cutting-edge research like the axis of evil provides valuable experience and inspiration for young scientists entering the field. Ongoing research helps ensure the robustness of our findings. By continually testing and verifying results, we build confidence in our conclusions and reduce the likelihood of errors or biases. Studying the axis of evil contributes to a broader understanding of the universe's isotropy. Determining whether the universe is truly isotropic on large scales has profound implications for our cosmological principles and theories. Ultimately, continued investigation of the axis of evil drives scientific progress. By challenging existing assumptions and exploring new possibilities, we push the boundaries of our knowledge and move closer to understanding the full complexity of the cosmos. In this video, we explored the intriguing anomaly known as the axis of evil. We began by understanding its discovery in the cosmic microwave background, CMB, and its implications for the isotropy of the universe. The axis of evil challenges our fundamental assumptions, suggesting a potential preferred direction in the cosmos. We discussed various hypotheses proposed to explain this anomaly, including foreground contamination, instrumental errors, and statistical flukes. Despite rigorous testing, the anomaly persists across different datasets and missions, prompting further investigation. The axis of evil has significant implications for cosmological models, particularly cosmic inflation. If the anomaly is real, it could indicate new physics or modifications to our understanding of the early universe. This has led to the development of new theoretical models and advanced simulations to explore potential causes. We also examined the role of large-scale structures in the universe, such as superclusters and filaments, which might be aligned with the axis of evil. This connection suggests that the early universe's conditions could have influenced the formation of these structures and the observed alignments in the CMB. Current research focuses on improving measurement techniques and exploring new observational data. Missions like the Simons Observatory and the Euclid satellite aim to provide more precise measurements to refine our understanding of the axis of evil and its implications. The importance of continued investigation cannot be overstated. By studying this anomaly, we can improve our knowledge of dark matter, dark energy, and cosmic inflation. It also drives the development of better observational technology and fosters international collaboration among scientists. Thank you for watching this in-depth exploration of the axis of evil. If you enjoyed the video, please like and subscribe to our channel for more fascinating content on cosmology and astrophysics. Be sure to check out our other videos for more insights into the mysteries of the universe.